Very good morning, everyone, and good afternoon, good evening to everyone from different places in the world. So, who joined us today? I am Aparna Kansal. I'm a systems engineer at Boeing and an executive committee member of the Incose India chapter. So, on behalf of the organizing committee, I extend you all a very warm welcome to the International Symposium on Artificial Intelligence and Machine Learning in Safety Critical Systems. So the International Council on Systems Engineering in COSE India chapter and the Aeronautical Society of India Bangalore branch and the IEEE Systems Council Bangalore section chapter jointly introduces the very first symposium of this kind in India. We sincerely thank our title sponsor Collins Aerospace, our platinum sponsors MathWorks and Boeing, our gold sponsor Honeywell, and silver sponsor LDRA for supporting the event. There is an increasing demand for safety critical engineered systems to inculcate human-like intelligence and autonomy. This demand is exponentially increasing. The complexity in the design, verification, and validation of such safety critical systems. So this symposium aims to bring together experts from multiple sectors, such as aerospace, automotive, and healthcare, to share their research findings and experiences on various challenges pertaining to the adoption of AI and ML in safety critical systems, including the implications on regulations and certification. So in the presence of all the eminent dignitaries that we have here and all the guests, let us begin this auspicious event with the traditional lighting of traditional lamp lighting ceremony.
Shubham kurutvam kalyanam arogyam dhana sampadah shatru buddhi vinashaya deepajyotir namostute deepajyotir namostute Shubham kurutvam kalyanam arogyam dhana sampadah Shubham kurutvam kalyanam arogyam dhana sampadah.
Thank you. Let us now commence the symposium by requesting Dr. Ramakrishnan Raman, the Principal Systems Engineer at Honeywell, Assistant Director for Incose Asia Oceania, and Chair for IEEE Systems Council Bangalore Section Chapter, to deliver the welcome address. Over to you, Dr. Raman.
Thank you, Aparna. Good morning, good afternoon, and good evening, ladies and gentlemen. It is indeed a momentous occasion, the opening day of the International Symposium on Artificial Intelligence, Machine Learning in Safety Critical Systems. This symposium is being jointly organized by Aeronautical Society of India, Bangalore branch, Incose India chapter, and IEEE Bangalore section Systems Council chapter. The Aeronautical Society of India, founded in 1948, is the principal society in India serving the professions in areas of aeronautics, aerospace, and aviation. The International Council on Systems Engineering, INCOSE, is a not-for-profit membership organization with a mission to address complex societal and technical challenges by enabling, promoting, and advancing systems engineering and systems approaches. IEEE Systems Council promotes, encourages, and supports the technical, academic, and application aspects of systems engineering and systems thinking. Today, I'm honored to deliver the welcome address for this event, beginning with the inaugural session. On behalf of the organizing committee, I'm privileged in welcoming the luminaries on the virtual inaugural session stage. It's my honor and privilege to welcome Dr. G. Satish Reddy, Secretary, Department of Defense R&D, and Chairman, DRDO. As a top defense scientist in the country, Dr. Reddy guides the development of major programs on missiles and strategic systems, fighter aircrafts, and unmanned aerial defense systems. A visionary and institution builder, his technology leadership has deeply impacted the development of best-in-class systems for the Indian Armed Forces. Next, it's my privilege to welcome Dr. Tessie Thomas, Distinguished Scientist and Director General Aero, DRDO. She has designed the guidance scheme for long-range missile systems, which is used in all Agni missiles. She was conferred with Agni Self-Reliance Award in the year 2001, and many more prestigious awards, including DRDO Agni Award and the DRDO Scientist of the Year 2008. A very special welcome to Ms. Kerry Lunny, Country Engineering Director, Thales, Australia, and the President in COSI. Kerry has extensive experience developing and delivering large system solutions, including combat systems, mission systems, communication systems. She has worked in various industries, including ICT, gaming, financial, transport, aerospace, and defense in Australia, Asia, and USA. Next, a very hearty welcome to Dr. Vincenzo Piori, Professor at University of Milan, Italy, and President, IEEE Systems Council. He is a fellow of the IEEE, Distinguished Scientist of ASEAN, and a senior member of INNS, and has published in over 400 plus papers in international journals, proceedings of international conferences, books, and book chapters. And finally, it's my privilege to welcome Mr. Savyasachi Srinivas, Executive Director, Collins Aerospace, India. He leads the engineering organization in India for Collins Aerospace in Bangalore and Hyderabad locations. He has global work experience in aerospace and defense corporations in the United States and India. He has led the development of many large-scale systems for mission-critical applications in aerospace, aviation, and other engineering domains. It's heartening to note that you have all allotted time to be present in this inaugural session of this symposium. Thank you. Next, it's my pleasant duty to welcome delegates and representatives from our sponsors. The title sponsor, Collins Aerospace, Platinum sponsor, MathWorks and Boeing, Gold sponsor, Honeywell, and Silver sponsor, LDRA. Without your support, it will not be possible to organize this symposium in a grand manner. And finally, I also welcome all the Indian and international delegates from industry, delegates from universities, faculties, and our next generation, the students, and all from the research laboratories who are actively participating in this symposium. Thank you all.
Welcome back, everyone. And now let us start with the symposium keynote address, the first keynote address. That would be by Ms. Kerry Lunny, who is the INCOSI president, as introduced by Dr. Raman. I invite you, Ms. Kelly, to present the keynote address.
Sure, thank you. Let me just share my screen. One moment. Can you see it? Great. Well, thank you, everyone. Thank you for the invitation, for participating at this great event. Apologies for the little bit of mix-up at the beginning there, but there is some technical problems, so I've moved further up the program while they're sorting out some technical difficulties. So what I'm going to talk about today, in line with the AI and ML learning in safety critical systems, I'm going to talk about the spectrum of artificial intelligence and machine learning awesomeness. And what I mean by that is the whole human acceptability of AI and machine learning. Okay, first of all, consider AI. Some people love it, some people are extremely in fear of it, and there's a lot of individuals in between. And it really comes down to there's a lot of difference of opinions, but the thing is that we need to be aware of is that it's not a golden chalice. We have to do things right. And I do like Stephen Hawking's quote up there on the top left. Success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last unless we learn how to avoid risks. And then you've got AI can be our friend, which is Bill Gates. And so there's fears and opportunities, and that's what I'm going to go through in this quick presentation. And some of the focus is pretty much on human imitative, and possibly that's a great distraction to AI. Who said that it has to be human-like in everything that it does? So we need to think of it from a complementary aspiration to human imitative. So I'll move forward now. Now, the spectrum of awesomeness And what I'm referring to is that you could be at the bottom of the spectrum, which is you're in complete fear of AI and ML. Going forward, I'll just talk mainly about AI, but I do mean AI and ML. So it can be 0% acceptance. And then you'll go through up the channel to the people that are in wonder and have 100% acceptance. And why is it quite polarized? In the red, you can see a lot of the challenges that are faced and the arguments that make people fearful, anxious, angry, things along the lines of there could be complete loss of privacy, blind reliance, the lack of human replication, and things along the lines too, the unintended consequences. And if we don't think about it too, we lose a lot of our mental capacity. I mean, how many people now remember phone numbers and addresses? We just dive straight into our smartphones. There could be greater implementation timeframes to do something through AI to create it in the first instance. There's a lot of reasons there. Now, if I want to dilute those negativity with some more positive, it's moving the blue funnel and infiltrating that into the red. And the sort of things that AI, or the positive effects are digital assistance, reduction in human error. We give increased productivity. We could use AI in robotics where it's safer for the robot to go versus the human being. And we can have 24/7 availability. There can be scalability, automation, and so forth. So I'm going to be talking about this spectrum of awesomeness. Now, how do we get there? And that's through a road of vision versus emotion. And I've put down on the bottom there, awesomeness means wonder plus respect and a little fear. And we need that little bit of fear because otherwise we could suffer from blind faith and complacency. And we do that, then we will make some errors. We do need to be very well aware of what we're creating for the greater good of mankind, to live in a world that we want to live in. And so that vision is we want to take things that might be completely unfavorable, move up to the unfavorable and apprehensive to something's favorable and balanced, and then something that is more favorable and hopeful. But we have emotions that get in the way. And these emotions can expand right down from fear, anguish, anger, contempt, sadness, so forth, right up to surprise, interest, joy, and excitement. And it can vary from individuals' perceptions. So here's a couple of examples. Bill Rouse said in his article in SMC in 2017 of what the impact is from driverless vehicles. Now, you could say that there's a loss of insurance companies for their main product line, most profitable product line. So from the insurance organizations, that would be a little bit of anger and anguish. But for the general public, we think, less insurance. So that gives us joy. You can also, with driverless cars, drill down to there'll be a reduction of around $200 billion in healthcare costs. That is terrific. That's great. It also is going to decrease organ donations because there's less car accidents by 25%. Now, that could be very bad news for someone that's waiting for an organ donation, but also at this point in time, we'll be having a lot of artificial organ donations. So there's pluses and minuses. Fewer service stations, less cars will be owned by people, and so on. So you can see how we can go different ends of the spectrum. Another example is a 2-year-long study by McKinsey has suggested that by 2030, robots will be replacing around about 30% of human labor, which means between 400 and 800 million jobs, which equates to around 375 million people have to get retrained and switch jobs. That could be huge and scary. But on the flip side is, and according with AI and ML, there actually will be more jobs created. It's again, reskilling and upskilling. So I'm going to use this case study to explain a few things on AI and the acceptance of it in that spectrum of awesomeness. And I'm going to talk about wildfire evacuations. Now, wildfires are unplanned and uncontrollable fires that are fueled by vegetation and at times can involve structures, housing, urban areas, but they're completely out of control, broad areas of the land it can start with. Now, this diagram is very simple. If we look at the fire conditions on the bottom left, of course, they're changing. The weather has an impact. Dryness, thunderstorms, dust storms, vegetation. Is it dry? Is it brittle? Insect infestations, topography, the slope of the land. All of those can lend to making some regions more susceptible to fire conditions. If we look at the top, we have planning and intervention. And planning is what we do before a fire happens. And then intervention is what we're doing when a fire is occurring, when a wildfire is occurring. So the information available, we've got a lot of Internet of Things, sensors, cameras, a lot more material on weather patterns, etc. So the planning is quite extensive. And the planners look at it from a point of view of how we are going to move the public for evacuation, where am I going to dispatch resources, what procedurals I'm going to set up, what emergency communications am I going to give, so on. So we've got an idea of planning and intervention. In the middle, we have the people, the residents or the general public. And that could be people that are transient or people that are living where the wildfires is occurring. And that how we behave is very different based on our education, our gender, our age, our economic, strength, from a point of view of infrastructure with communications. Do we or have we lived through a wildfire before? And is it just our homes or our livelihood that's at stake? Because if that's actually under threat, it's a big difference between leaving a home and leaving your area, your business, and then the population resources to support all of that. So we look at that from the residents. Now, if I'm evacuating, in most cases, it's going to be start off as a pedestrian and then add to a mobile or car to actually move you. So we've got traffic conditions. And what does that mean? From a point of view, what's the infrastructure already there? Do we have roads? What is the width of the roads? How many roads do I have? How many bottlenecks, bridges, one way? The traffic performance, what's the steady state mode of that traffic in that area? And then it's going to be inundated with extra residents evacuating through a wildfire. So all of that is very much a safety critical system, and the balancing act is very huge. Now, if I'm going to throw in artificial intelligence into that in a moment of complete stress for individuals, how's that going to be accepted? Will I actually be able to feel that wonder and feel comfortable, or I'm going to be more fearful of that? And if you consider the picture on the right-hand side, did they ever think of that when Australia was burning in 2019 and 2020? Biggest fires ever recorded in the world, and still have. The landmass that was covering was the equivalent of the UK, was equivalent of Belgium, Norway, Sweden combined on all fronts. And what that picture that they didn't think of too is at the time that the fires were burning, in the second half of that burning, we got hit with COVID. So we've got the country under fire and COVID coming along in the February and March of 2020. And that picture there of that girl in the boat, that's taken in the middle of the day. And it was taken in the middle of the day because this fire was happening around our major holiday period in a rural area on the seaside. They couldn't get out on the roads. They all went down to the beaches, and then that got filled. And before the Navy could come in, people were coming in boats to get people out of the way. They never thought of any of that in this wildfire scenario. So really extreme circumstances, extreme weather. Population was 4 times the amount that it normally was. Roads completely blocked, no way in, no way out. And there we had water on one side. So interesting. Then how would AI would have helped us in that scenario? Now, the sort of things then that we need to think of is arguments and activities that are going to support the adoption of AI and ML. And what's going to support the adoption is along the lines of demonstrating credibility, trust, reasoning, social acceptance, and the basic need for safety and security. And what I've tried to show here in a number of categories is then topics that would lend themselves, or topics, arguments, and activities that would lend themselves to demonstrate one or many of those combinations that I've just stated. So I'll give a few examples that you can see on the screen. We've got ethical AI. And what does that mean? From an argument or activities, you would think of governance, traceability, and the legal or law. Now, from a governance perspective, the general public is going to think of that is a trust perspective and social acceptance because of the governance. Traceability gives you the argument for reasoning, and the legal side gives it credibility. Okay, so that actually makes it okay. That might be more acceptable if I can show governance, traceability, legal to support ethical AI. If I look at the data-rich environment there, it's arguments and activities to help. It means I can make faster decisions. I can use a trusted source of that data, and the data can be used for augmentation of other activities or the human consideration for whatever they're using that data for. Now, that would lend itself to credibility and reasoning, and they are very, very powerful. If I look at situational awareness, arguments I could use there is that I can actually demonstrate through a number of verification validation. And if I'm completely giving more information to situational awareness, then I can increase the determinism. So I can move away from things that are less unintended or less non-deterministic to increase. Won't necessarily being fully deterministic, but it will move along that path to increase the determinism. And I can actually do a lot of what-if scenarios with adaptive behavior. Now, how do I sell that from the point of view? Well, that adaptive behavior gives a lot of sort of sound reasoning and credibility. Increased determinism also gives a good reasoning, and then social acceptance. Trust is trust. And then, you know, verification and validation goes back to the basic safety and security needs. If I move across to the right-hand side of the screen, what about from a point of view of resilience? And what does resilience mean? You know, you're going to fail. You need to accept that, but it should be able to be recovered whether in fully recoverable or into a degraded mode of operation, but still recoverable. So I need to think along the lines of being cyber resilient, robustness, survivability, durability, and continuing the operations. Remember, one of the arguments is we could operate 24/7 as an example with AI. So again, all of those give a level of credibility, trust, reasoning, and social acceptance. If I go to the decision aid, and this is a lot of work is being done at the moment with complementary or augmented artificial intelligence, where it's helping and augmenting the human making the decision at this stage. Models and simulations, performance monitoring, I would say predictive maintenance, that the turnaround to correct things, and then the comprehensive data analytics associated with it. Data analytics lends itself to credibility and reasoning. Predictive maintenance, credibility and reasoning, and safe and secure. The turnaround time lends itself to credibility and reasoning again. Performance monitoring the same too. And the models and simulation can also lend themselves to social acceptance because you can demonstrate things that people have a better understanding of. So these are just some areas that I'd see as arguments and activities to support the adoption of AI. So what does that mean? If I now move back into my wildfire evacuation case study, here is some areas where the future addition of AI and ML can lend themselves. So I'll go back to the fire conditions. we can have improved predictive patterns. And let's face it, the weather, the climate change, things are becoming more unpredictable. Occurrences are happening more often of extreme. There's no more of this 100-year flood or 100-year fire. Yes, now it's happening every 10 years or 20 years and getting smaller. Increased warning times. Think about that, you know. So if we can have the sensors out there that is measuring more of the moisture readings below the Earth's surface, on the Earth's surface, just above the Earth's surface. If we've got more sensors out there, we're looking and monitoring the insect infestations, the vegetation growth, that will give us more indication. And the urban sprawl that's encroaching in these wildlife areas. Again, that's actually going to help us understand what evacuation plans might need to look like. If we move now into the planning and intervention area, we have a lot more IoTs, a lot more sensors. We've got the 5G out there, and goodness knows what it will be in years to come. We'll be able to do a lot of rapid what-if scenarios, which is extremely important. Now, there is Professor Fang Chen at the University of Technology in Sydney is an AI and data expert, and she's designing AI systems that can recognise when humans are reaching their cognitive limits. And she's actually working on how people perform when they're under stress and overloaded, and how to develop AI systems that can adapt to help that. And she's doing that studies through bushfire management, which again is under wildfires. And it struck that, you know, under bushfire management, what's the balance that you need to give to the operators to have the right amount of information so that they can make the right decision in emergency? And particularly when you're talking about bushfires or wildfires, they're occurring in multiple areas. And then you've got multiple considerations that are quite unpredictable and changing all the time with the weather. And you've got to dispatch resources to where, you know, what location or multiple location and so on. So you're going to have extremely moments of stress and overload. And so they're working on, well, where can AI help plug that gap, shall we say, and also recognize when the person has gone through that level of stress and is back on working at a high performance level to make the adjustments. That is really phenomenal work. That helps also with the real-time situational awareness. Of course, if you've got more data, you've got better analytics and visual analytics that you will need. Think of a mobile command and control center or centers that will have distributed, which is more than just having a satellite radios at this point in time. Firefighting UAVs, you know, we at the moment have the helicopters and the planes that go and bomb water bombs in those areas. And we've got people on the ground, but looking more on the robotics and the drones that will help take over. A lot more models and simulations using augmented reality and virtual reality. And of course, when you're doing all this, your cybersecurity has to be very strong. We've got to protect, detect, and recover, respond and recover. We've got to think of things too, you know, where location is critical. So we need to have some very strong jam-resistant navigation systems. If we move now to the resident side, things can be a lot more personalised with AI and ML if it's accepted by the public. So we can have unmanned evacuation systems, particularly personalised for where that person lives. What is the demographics of that household? What is the environment around that household? Can they have a personal warning system that works for them? And I'm not just talking beeps and alarms that could be personalized, but specific messages. And so for your warning system, instead of saying, you know, everybody in this street or this area or this location, you've got half an hour to move to another location, it might be saying, hey, Fred, you've got 15 minutes, but it's better that you go to the end of your property versus going to the evacuation center because the winds are changing and your topography says otherwise. We can use virtual reality to help them understand all this. And then even from the point of view, depending on the demographics of the residents, we can have autonomous vehicles or driverless vehicles going into the areas, picking them up and moving them, evacuating them to a safer location. Okay. Think of traffic conditions from that perspective. We can have a better flow on the traffic because we get more real-time information. And if we're giving more personalised evacuation, we might have a greater dispersion of the traffic in that area. We could also, as I said, talk about using new modes of UAVs and assisted transport. And that's in a very general term. But if I now look at this slide, what I have here in the diagram in the middle is a typical life cycle of activities for evacuations. You prevent and mitigate, then you prepare, then you respond and you recover and you integrate. And in each of those areas, there's some examples of what that means. So if I add AI to this as an example, I could have under prevention and mitigation, vulnerability assessment trade-offs, extremely important. Under preparedness, I could have personalized evacuation simulations. So in a household, they could put on their virtual reality goggles and have a layout of their property, and they could do different simulations on fires coming in on different fronts, and they could practice in simulations in virtual realities. If I moved on to the response, I can use driverless vehicles to move residents out of harm's way, particularly some of the elderly that might get a bit confused. In the recovery side, I've got more data. Let's see what we can do to help us with our vulnerability assessments in the future and our predictions. And of course, if I'm working with other services and integrated, let's have some virtual reality exercises to help improve our performance. But under all this, it's the human behavior that's the heart of accepting AI and ML. So who's responsible for reaching this level of awesomeness? Well, it's anyone that's carrying out the systems engineering activities on the solution, whether it's a product, a system, or a service is being offered. And whether you're called a systems engineer, an architect, a project engineer, a solution engineer, it just depends on what industry you are. But you are the ones that are looking at it holistically and need to take into consideration then what all of the stakeholders might need to move us to a vision that's favourable, balanced and or hopeful. So how do we do this? The systems engineering role is made up of, to create engineered systems, has 6 elements to it, which you can see in that diagram: people's, products, services, information, processes, and natural elements. Now, some of the key AI, ML, SE capabilities will be changing in the future. So here's some examples. Under information, we need to know more on data analytics, expert knowledge systems, authoritative analysis, because you're not going to be able to prove everything through V&V. So analysis side, we better understand and get a grasp on cybersecurity, decision aids, autonomy, social engineering, huge, sustainability, and let's look for patterns and anti-patterns. The sort of processes that will change would be intelligent configuration management. You can just ask the system, you know, what were the changes and why, moving from version 1.2 to 1.3. How wonderful that would be. Decision justification support systems, digital twins, adaptions and automations. And then we need to look at those key stakeholders. And this is where it can change. And I'll just talk about that in a minute. And the user-centric designs, and there could be very more. So what that does it mean for us? We need to require and adopt a digital adoption. So move in a more agile manner. Data is key. Controlling, creating, protecting that data, sharing that data. We need to upskill. Okay, we need to learn more on analysis, the digital technologies, new V&V techniques, which is where that authoritative analysis comes into it. You can only show it through analysis. You cannot prove it through V&V. Verification and validation is what I mean by V&V. We need to be much more flexible, and there's going to be new relationships between the decision makers. So basically what we mean is that we need to recognize that decisions should be made by those closer to the issue. So it's not necessarily where it is now. It's going to be where it's closer to the issue. So it could be on the front. And then education and training needs to support these changes. So if I'm going to improve the safety of complex or critical systems, I've got to recognize that I'm going to have a diversity of solutions. It's got to have to be resilient, accept that it will fail, but it needs to be able to recover. And as I said, accept that you've got new relationships with key stakeholders so that the decisions are made closer to the coalface where the issue is. Now, if you want to be all part of this, I'll just give a little advertising for the International Council on Systems Engineering in COSI. We have a number of working groups and across the world. So we have over 19,000 members and associate membership across different countries around the world. We have a number of working groups. We have over 50 of them. We're looking for solving problems, creating technical products, and influencing standards and a lot of other initiatives around the world. On the right-hand side, you can see an example of some of our working groups. And what they're working on varies. We're looking forward always. And so in the AI working group, they contribute to the international community. They carry out related AI research. Presenters present at events globally. And you will hear from a few of them over the next 2 days. And we look at supporting related articles and publications. So the Systems Engineering Vision for 2035 will come out in January and February next year. AI has been involved in helping authoring that. And the Systems Engineering Body of Knowledge, a number of articles have been written by the AI community. So if you're interested, look us up on the web at www.incosi.org. You might be interested in joining. But for now, if you're still not quite sure, you might want to join us at our workshop in January. We hold one every year. It goes for 4 days. And our international symposium, which is at the end of June next year in Detroit, that runs for about a week. All of them will be hybrid events, so you can join physically or remotely. So it'd be great if you can join us and contribute to the world of AI. But I'd just like to end with this one quote. It's one of my favorite ones by Eliza Yudkowsky. By far the greatest danger of artificial intelligence is that people conclude too early that they understand it. Thank you for your time.
Thank you, Ms. Lani, for the wonderful keynote address. It gave a very good understanding of AI over various domains and all the areas it can be useful and what the future of AI is and the challenges in its adoption. So it was very interesting. So sorry about that. I think Dr. Satish Reddy is facing some issues with connection. I would like to now call upon our title sponsor, Collins Aerospace. We have Mr. Sabyasachi Srinivas from Collins Aerospace, who is the Executive Director of Engineering in India. We welcome you and thank you. Thanks a lot to Collins, who are our title sponsors. And I invite you now, Mr. Sabyasachi, to give the title sponsor address.
Thank you, Aparna. Good afternoon, everybody. Let me just quickly share my screen. And once I do that, if you can please quickly confirm if you can see it, that would be great. Let me know if you can see my screen.
Yes, it is visible.
We can. You can go to the presentation mode. Yeah.
Thank you very much. Good afternoon again. Thank you again for having me at this forum. It's a pleasure and honor for me as well as Collins Aerospace to be associated with this forum and looking forward to our continued engagement in the future. So with that, before I start my talk, I want to give a little bit of an overview of Raytheon Technologies as well as Collins Aerospace. As some of you may or may not know, this was a company that was formed less than 2 years ago. So I don't know how many of you would know what the company does and what we do at Collins. So just a few slides here introducing you to the organization, and then we'll slightly get into the details of the presentation. So as the name suggests, we are Raytheon Technologies. We came together as a merger between Raytheon company as well as United Technologies, now almost two years ago. And it was a merger of equals. And what we have is a very large aerospace and defense company now with almost 200,000 employees globally, about 200 years of combined innovation and leadership experience in this realm. Financially, about $75 billion. This is, of course, pre-pandemic. Obviously, the aerospace and defense industry went through some challenges after that. But significant investment in R&D as well, almost $8 billion of R&D funding on an annual basis. And we have several R&D centers and enterprise global centers, capability development centers across the globe. Greg Hayes is our CEO and Tom Kennedy is our executive chairman. More to the next slide. Raytheon, like I said, is a conglomerate of multiple organizations, all aerospace and defense. And some of the names that you see are big names in the industry. Collins Aerospace, who I represent, and I'll talk to you a little bit more in detail about Collins. But then we have Pratt & Whitney, who's one of the pioneers in engine manufacturing. And then we also have two other companies, sister companies, Raytheon Intelligence and Space, and Raytheon Missiles and Defense. And as the names would suggest, Raytheon Intelligence and Space focuses on our intelligence and space community and works with the customers there globally. And RMD focuses on the defense and offensive side of things, including missile development and manufacturing for our customers globally. Okay, specifically about Collins Aerospace, we have about 80,000 employees globally and annual revenue of about $26 billion, headquartered in Charlotte, North Carolina, and have a very large global footprint. One way to say what Collins does is anything other than the fuselage. We don't build the actual structure, but we have nose to tail capability in every aircraft system that is involved in making the planes fly. So if you look at it from our business unit perspective, we have 6 main business units. Aerostructures, as the name suggests, deals all with structures. Our big product there is the engine nacelle, and we have our nacelle product on several of our platforms, including our partners in Boeing, Airbus, as well as some business jet aircrafts as well. Avionics, again, a lot of capability, in the cockpit, including flight management systems, flight controls, the entire cockpit display, heads-up display, and also, weather radars. We've got flight control systems, we've got, navigation systems, and so on. So the full suite of capability there, and we have our flagship product called the Proline Fusion that is very popular with our business jet customers. Interiors is an interesting business that we have. This deals with more the creature comforts on the plane. We have our very renowned products on board, first class, business class jet segments in terms of aircraft seats. But we also do veneers, we do galleys, inserts, oxygen systems, evacuation systems, and so on. So again, a full suite of capability, both in terms of comfort as well as safety of passengers. The fourth business division, as I said, mechanical systems, again, as the name suggests, has to do with all the mechanical components of the aircraft, including, landing systems, wheels and brakes. We've got cargo systems as part of that, as well as actuation systems. Mission systems is where we support our military and space customers. A lot of support to our military customers globally, and we have extensive relationship with militaries across the world. And last but not least, we have power and controls, which is another business unit, and this obviously is the part that keeps the aircraft powered up and allows us to keep the power on the plane. So that kind of covers all the major business units of Collins Aerospace. Just wanted to touch upon the legacy of innovation that we have as part of Collins. Some of the names that you probably see are no strangers. They are stalwarts of aerospace, whether it be Arthur Collins from the Collins Radio time frame to David Sunstrand, to Thomas Hamilton, Goodrich, Rohr, Bratier. I mean, these are some of the stalwarts, like I said, of the industry, and have left such a mark on the industry. And today, we still enjoy some of the work that they did, in their prime of, when in their careers and the innovation that they produced. And that is a legacy that we have as Collins as a company, and very proud of that legacy. And as we move forward, we are focusing more and more in terms of digital transformation. So this subject of AI, ML, data analytics, connected ecosystems is very much, I think, a focus for us. And like I said, very, very happy to be part of this forum, not only to share our views, but also learn from all of you in terms of what is going on in the industry. So specifically in terms of artificial intelligence in aerospace and defense, AI/ML as a technology is nothing new. I mean, we've seen some of the work started off in even in the 90s. I will let you in a little secret. My master's thesis was in neural networks as well, but I won't date myself by giving you the actual year. But it's been around for a while. What we saw is since 2010 is when we have seen more of a revolution in this area and adoption in multiple industries. You heard about Ms. Kerry talk about driverless cars and so on. So aerospace and defense has never been, I would say, a quick adopter of technologies. We usually take our time and you apply it only when it's fully proven. And there's a reason for that, because it's a safety critical system, and lives depend on how we sort of implement these applications. So it is with good reason that we spend a lot of time in validating and assessing these technologies before they are implemented. What really has accelerated it is in 2018, the Department of Defense AI strategy directed the acceleration of adoption of these technologies across all military domains, and the Joint AI Center was established. So that's really gaining a lot of momentum in terms of
pushing the industry forward in terms of adopting these technologies, be it in terms of connectivity, access to data, and building safety into the systems. These are all areas that are gaining a lot of traction. What we anticipate is, over the next 10, 15 years, we will see a huge explosion of adoption of these technologies in the military as well as civil aviation domains. And the reasons are there, and we talked about that. Other speakers have spoken about it, but clearly there are clear advantages in terms of significant reduction in the overall life cycle cost by bringing in these technologies in, especially with DPLC, combining these with DPLC related processes, as well as reducing cycle time in our whole life cycle of design, simulation, prototyping, all the way through manufacturing and upgrade. So really exciting sort of time for us. And like I said, we'll see an explosion of these technologies and their adoption in more and more applications in AI and in aerospace and defense. This presentation is not meant to be in any way a deep dive into these technologies, just giving you a little bit of a high level overview of where some of the applications are and some of the work that is already being done. Again, this list is not very exhaustive. There are several more applications that are being worked upon, but some of these are gaining a lot of traction. Clearly, when it comes to civil aviation, autonomy is something that is being spoken about a lot. With the amount of work that a pilot does while navigating a plane, the focus is on how to reduce crew operations, how to get into single pilot operation, and potentially even autonomous, completely pilotless sort of operations in the future.
And this is where I feel AI/ML will have a huge role to play. And there's a lot of work being done by multiple aerospace and defense companies in this area. The second area I want to highlight is intelligent systems. Again, if you look at it in terms of how you control, navigate, safely through different environments. We are beginning to use AI/ML, quite a bit. Performance optimization, with fuel prices going up, more and more airlines are now focusing on more efficient operations and using algorithms that can help you with your climb rate or maneuvering through weather. Coming up with more optimized flight plans only will help you save more fuel in the future, and clearly is an interest to our customers. So that's an area that is definitely of interest to us and as well as other like-minded companies. But even if you look at it in terms of defense, be it battle management or how to use it in cybersecurity, there's a lot of research going on in these areas as well. Materials and manufacturing, again, be it in terms of computational materials or advanced manufacturing, we are seeing some utilization of these technologies. Predictive methodologies, especially if you look at it, maintenance. Predictive maintenance is clearly an area where AI/ML has already made significant inroads and helping reduce downtime of planes on the tarmac when there is a repair going on. So coming up with the accurate and predictions of when the maintenance needs to happen and doing repairs and overalls has been something that AI and ML technologies are already being used. But we soon start seeing these getting into our engineering processes as well in terms of design, and verification. And to move forward to the final leg is the complete digital transformation and using it with higher computational power as well as cloud enablement, more and more utilization in terms of PDM, PLM, using digital twins to kind of mimic the physical sort of environments is something that you see a lot of work being done on. In terms of challenge, of course, since these are all highly data dependent, having high quality data and availability of algorithms that can be used as well as scalability and maintainability become key issues that we need to look into. The next section, I'm going to give you a few examples of where AI/ML is being successfully adopted. In some cases at the early prototype, as well as in some cases where there are deployed sort of systems. The first three examples are from Raytheon Technologies. So if you look at the first one on the left here, it talks about digital twin and how that is being utilized in battle management system using AI/ML for performance predictions. Being able to sort of manage your in-flight trajectory of your missiles. So to simulate the whole battle environment, creating real-world scenarios and testing out your equipment. So those are things that are actively being pursued by our RMD division. Another example I want to give is this Lynx Infantry fighting vehicle, which is essentially a tank. It is supposed to have 3 soldiers in it. What's been done is now it's got 2 soldiers and a third virtual crew, which is basically AI, and sort of helping up, with making decisions on the fly and helping support the 2 soldiers who are there to make real-time decisions. The third one that you see on the right is a Collins product, which is an Essentia analytics service, which is basically prognostic and health monitoring onboard components for preventive maintenance. And by using this system, airlines across the world are reducing the cost due to flight delays and cancellations. So these are systems and various levels of maturity that are using the AI/ML framework and technology. Some more examples, Airbus, and this is more from the other industry as well. Airbus using
AI/ML for fully automatic vision-based, takeoff and landing. And this demonstration was done as recently as 2020. And it used AI-based controls as well as image recognition software to be able to manage such, complex maneuvers. The middle one, again, is very interesting, which is basically a pilotless, crewless aircraft operating with, completely coordinated control using AI on board, and use of AI algorithms to teach the onboard computers to be able to, again, perform such complex operations is just mind-blowing, and it just opens your mind to what else may be possible in the near future. The last one is, again, application, again, by Boeing, on drones. Again, move on to a few more, which I want to get into off the plane now. Look at in your airports, and these are, again, Collins-specific applications, and essentially improving the overall passenger experience, in how you enter an airport, how you check in, to baggage drop, to security, to kind of immigration, and finally boarding of the plane. We are bringing to bear of the technology in all these different phases of wherever systems interact with the passenger. So be it in terms of softwares and algorithms that will do face recognition, biometrics, and basically enhance the overall sort of experience of getting on board a plane and deboarding and getting back home. You see some pictures of our AirInc automated border control where there's nobody manning it. It's completely completely automatic. All right. The next one is, again, an airport sort of demonstration. This again is again handling of all our baggages, and if you've been to some of our busy airports, you know how many baggages are handled. This is bringing in AI/ML to track, essentially identify, track, and handle the baggage throughout its time. From the time the passenger drops it off till they collect it at the destination airport. In terms of again using smart baggage sort of management systems, assisting in more smarter self-drop and check-in sort of systems, and lastly, sorting of baggages and making sure that none of the baggages are lost or rerouted to wrong sort of destinations, which I'm sure has happened to many of us in the past. So this is all practical areas where AI/ML is not just being talked about, but actually being implemented and being fielded in systems across the world. Lastly, I want to just end with a quick slide on what the challenges are ahead of us in terms of adopting these technologies going forward. Clearly, we have to see where just because we have a very powerful tool doesn't mean we can apply it everywhere. I think there has to be a lot of focus on safety, especially as an industry like ours that has to be the prime sort of motivation for us to apply it. Yes, there are advantages, but we have to sort of balance that against what risks we'll be bringing into the system. So identifying and validating the models before sort of applying them, understanding the robustness of the algorithms that we intend to sort of apply to making systems more smart. Clearly, when you're looking at aircraft, we don't have unlimited capacity in terms of computational resources. So more efficient and optimized way of utilizing these technologies where we use minimal resources is going to be something that we will be researching in the future. More and more focus on how do we integrate, test, and certify these systems. I know there's a lot of talks which are scheduled tomorrow on and esteemed panels talking about certifications. I'm really looking forward to that. But that's again going to be an area that we will need to research more.
cybersecurity, again, goes without saying, is going to be very, very critical. And we need to make sure there are, by implementing some of this work, that we don't bring in more vulnerabilities in safety critical systems. And lastly, I think it's more about the people. How do we scale up our technical capability and competency to work on such systems so that we are able to take them to the next level? So again, world of exciting possibilities ahead of us, not only in terms of the aerospace and defense industry, but across the globe in multiple applications. It'll be great to get into a world where AI ML kind of becomes ubiquitous in a plane or any environment associated, an airport or whatever, where it is like an Alexa, Siri, or a Cortana, where you have so many of these aids and devices helping out improve the overall experiences of not only the passengers but the users and the customers. And that future is not very distant. I see that happening very quickly with adoption of these technologies, and there's a lot of emphasis on building this capability as well. And together as an industry, I think we can make sure all the safeguards are put in place where we can safely implement these technologies going forward. With that, thank you very much. And again, I appreciate and thank INCOSY, IEEE, and Aeronautical Society of India for giving Collins and myself an opportunity to interact with all of you, and looking forward to a very exciting next day and a half of presentations. Thank you very much.
Thank you so much, Mr. Sarvasati, for this very insightful session on very interesting applications of artificial intelligence, which are currently ongoing. So I would now like to again call upon Dr. Satish Reddy to give the chairman of DRDO to give the chairman the chief guest address for today.
Thank you. Good afternoon and good evening, everyone who is present there. The Aeronautical Society of India, IEEE, and all others who are actually the people behind this symposium, which is an international symposium on artificial intelligence and related subjects. Firstly, I'm extremely sorry. My apologies to you for not being able to join at the time what is given to me. As there was a meeting with high level of people here with the members of parliament and Raksha Mantri. I couldn't join at the time. There was a meeting called at the time. So my apologies to all of you for this being not able to join the meeting. Firstly, many speakers who would have spoken before me would have actually brought in the importance of artificial intelligence in the today's scenario. Even though AI is a subject which has been brought in, I think, early 90s or around that, and it hasn't picked up the way it was supposed to have, even though we talked about various languages and people started learning about it and things like that and all that. But then it has gained its importance now in the last couple of years. Everybody talks of it and everybody is trying to implement, and many things are happening in this. As you all know, the DRDO has a laboratory in Bangalore called Robotics, which is established, who have been working on AI since long, along with robotics. It's one of the important laboratories working along with the armed forces and security agencies for various applications in the area of AI, for various systems and software and analytics, whatever they're developing and trying to put into that. So one laboratory. Second, actually, there is one young scientist laboratory, which is again established in Bangalore. It's the direction of the Honorable Prime Minister, Sri Narendra Modi ji, that there should be young, all the people will be below 35 years old. So this has been established, which is there in Bangalore, areas where AI-related things. In fact, I like to mention here that AI particularly is very important for the systems which are required for the defense and security agencies related applications. Very important. A lot of serious applications which have been there, whether it is, let's say, the image related applications or vision based applications, which particularly for the security agencies, a person whom you are trying to identify, and then you have all the systems, and because it's extremely difficult for manually to correlate everything, and you want to identify a person who has disguised a little differently and whatnot and all that, still you are able to identify using all the mechanisms possible with AI is one of the very important applications. Likewise, if you talk about the voice and text-based various applications, the data which comes in, hell of a lot of data which we'll be able to get, and you are trying to analyze that, is another very important area which actually required for the security and defense agencies, defense forces in the country. Similarly, a lot of things, every system actually which comes out for today for defense and security applications need to definitely have AI features. In fact, DRDO has been working on this, and now today I have told all my system laboratories which are working should have an AI group in each and every system laboratory, and all the systems which are coming out should be incorporated with AI. Is one important decision what we are taken, and that every lab there is an AI group which has been created who are working, and as I said, the laboratory in Bangalore CARE is actually working with all these laboratories, providing the necessary know-how and directions how they can go ahead and all that. As I said, very important. See, very aptly chosen that for the security related applications today. Just talk about either a border surveillance system or talk about a perimeter surveillance system. It's very important with all the types of sensors what you have, whether you have got a RF sensor, you have a visual sensor, or you have a IR sensor, or you have got a fiber optic sensors and all that. When you have the sensor information, when you're processing and to get an information, you are trying to derive from that, and trying to have the actual correct, right information without much of false alarm, that then there is a real intrusion which has taken place, and the intrusion is not out of any animal or our own people and things like that and all that. We have to be very accurate, and that is where we need to incorporate in those things the AI and see that you are able to get the right information and right alarm to the people for them to act on. So this is sort of a thing. So you talk about anything today. See the type of surveillance what is required. If you're talking about either visual or image-based surveillance, or you're talking about IR-based surveillance, both are image applications, or you're talking about electronic intelligence, you're talking about communication intelligence, the systems what are based, ground-based or airborne or whatever it is, the systems. It is very important you are able to get this lot of information. You are able to really process them with all AI algorithms to date, and you are able to identify the right object. You are able to pinpoint the actual target, and then you are able to give this information, disseminate the information. Is one of the very important things in a warfare or any security related applications. Information gathering or surveillance is one of the most important thing. And then when you're gathering all this information, how do you actually assimilate all this information and derive the right thing and give the correct identification is one of the most important things what need to be done. If you just talk about, we are talking about a missile and a fighter aircraft, you are talking about a bomb and a fighter aircraft, are talking about the various sensors which go into the fighter aircrafts, various other systems, it is very important to have the AI features in the given scenario, and we have to see one thing. When the world is moving fast in a direction, we should not be lagging. When we are talking about in the universities, that is one of the things where the subject had been introduced in various universities. Programs are there. MTech programs in the cyber security and artificial intelligence are in the BTech as AI as one of the subjects has been introduced in many engineering colleges and universities today to produce a lot of things. In fact, actually, we are trying to mentor many startups and MSMEs in the area of AI. The Center for Artificial Intelligence and Robotics has taken a required for defense. AI becomes, cybersecurity becomes one of the important areas where we are trying to support the industries, fund the industries for research and development days. So that is one of the areas which actually we can fund industries up to 10 crore rupees in coming out with technologies, defense forces in the country. In fact, there is another scheme wherein it's brought out purely for youngsters. Just a graduate who is passing out today, if he is connected to the incubation center in that university, and he wants to work on a problem, and through that incubation center, we are ready to fund immediately, very quickly, in up to 1 crore rupees. This is another scheme through incubation centers, and most of the youngsters in the area of artificial intelligence, cyber security, and related aspects, people can utilize this opportunity and come up in a big way. See, the way is particularly the startups. So without taking much of a time, I actually congratulate the organizers for conducting this event for this. And then I like to see that a lot of people come up in that area, and a lot of people work for the security agencies and defense forces of this country with many of your ideas and the technologies and products related that are coming out. And we are there to support in a big way. And please see the website of DRDO, wherein this many schemes have been introduced. My best wishes to the conference, symposium, and I wish that the symposium will be able to come out with concrete ideas and mechanisms and processes, what needs to be incorporated in the country, the country progress in a big way in the area of AI is what I request.
I think we lost Dr. Satish Reddy's voice there. Looks like some connection issues. But yes, I think it was towards the end of the talk. So thank you, Dr. Satish Reddy, for the wonderful talk, and welcome to the symposium. Next, I would like to call upon Dr. Vincenzo Puri. He's the president of the IEEE Systems Council, as introduced by Dr. Raman. I invite you, Dr. Puri, to give your symposium keynote address. Thank you.
Ladies and gentlemen, good afternoon. Namaste. It's really a great pleasure to be here with you today and talk about some of the mission critical systems that are around us and are really contributing to make the difference in our life. In order to improve the experience in these systems, the ambient intelligence is a set of technologies that together can really help in making the difference and creating a unique, personalized, seamless experience to users. So what we are going to see is which are the technologies that we need to consider and put together in order to understand the environment, understand what is happening in the environment, understand what the users in the environment needs, and adjust the behavior of the environment. And we are going to see how we can use artificial intelligence, machine learning, data mining, as well as other techniques like biometrics and cloud, fog, Internet of Things, cyber physical systems to create the infrastructure supporting ambient intelligence in safety critical applications. Ambient intelligence is a set of technologies that we can deploy in a pervasive way in the environment in order to have a simpler, more natural, more human-like interaction between the humans and the systems. In addition, this kind of technologies are conceived to ensure that the environment itself is able to provide livability for the environment in an autonomous way. So we expect that this environment itself look to the people in that environment, understand the needs and the preferences of these people, and then automatically adjust its own behavior to satisfy these needs. So basically what we wanted to have is an infrastructure to create a smart environment to support a smart living of people. In order to achieve this goal, we need to be able to have an infrastructure which is able to understand, to observe the need of people, to understand the need of people, to learn directly from what the system is observing, what the people in the environment are doing, which are the preferences that they are expressing, in order to configure properly the system, in order to enrich the list of the needs and preferences of each individual with what the system just learned. And we need also to have a system able to dynamically adjust its behavior to the need of the people. And we need to have a system which is able to monitor what is happening, to monitor the evolution of the needs and preferences, and eventually to predict the future needs and the preferences based on the needs and preferences that have been expressed in the past by these specific people, and also considering the needs and the preferences that has been expressed in the past and the trend of people with similar characteristics. How we can do this? Well, artificial intelligence, machine learning, pattern recognition are essential tools which allow us to observe the world, understand what is happening, and extract the knowledge about the status, the evolution of the world, the status and the evolution of the need of the people, their action, in order to take appropriate decision about the management of the environment itself. And of course, we need to base this analysis on the real data extracted from the world. So we need to perform signal image processing from the data collected from the sensors, as well as we need to analyze the data with data analytics and data mining techniques, especially when we have other heterogeneous sources of data coming from different kind of mobile or fixed devices. The problem that we have is how we can associate the preferences, the needs to each specific individual. Basically, what we need to do is to characterize each individual. In the past, we have been used to adopt tokens, login and password, but in order to make this experience much easier for the persons, what we can do nowadays is to use biometrics as a technology which allow us to be identified, to identify the behavior, to identify the group of the individuals that we are considering and who are sharing similar needs, similar preferences. So basically what we can do with biometrics is to uniquely identify an individual so that we can profile the individual, we can record the needs and the preferences of such an individual, and then reuse later this information to personalize the environment in which the individual is acting. Similar, we can identify the group of people with a similar characteristic, not necessarily the specific individual, but for example, young people, old people, men, women, and if they share some characteristics, some needs, some preferences, we can associate these needs to all people with who belong to that group. If I have an elder people, maybe an elder person, maybe he or she has difficulties in crossing the road, I may want to recognize when I'm managing the traffic lights, this person, so that I can extend the green light and facilitate crossing the road. Or I wanted to identify just the behavior, the gesture, the facial expression, the emotion, so that I can also use this information as comments or as feedbacks to the behavior of the system. All of this will allow me to create a profile for the individual or the groups of individuals, and as a consequence, be able to create personalized services. To support all of this, we may need to have infrastructure capable of collecting the data from the sensors and bringing the control signals to the actuators in order to ensure that the entire environment is properly managed. And for this, we have nowadays Internet of Things or the cyber physical systems, which are typical model to achieve this purpose. In addition, we may have a cloud, fog, edge computing in order to store the data, to process the data, to store the algorithm, to process the data. But let's have a quick look to what we can have as a smart environment in order to support the safety critical systems. Well, typical system of this kind, typical application of this kind are, for example, in the electric power generation, transmission and distribution, where we wanted to ensure the proper distribution of the energy to people and to manage in an adaptive way this type of environment, ensuring, since this is very critical for the life of people, for the economic activities, and for the social interaction. Similarly, we need to protect and manage the oil and gas pipelines, as well as the water and distribution and the waste collection. All of this infrastructure are increasingly important in our modern life, and we need to ensure that they are properly monitored and protected, and their control needed to be adjusted according to the needs of the people. People may not interact directly with this kind of infrastructure, but these infrastructure are bringing resources to people, and as a consequence, the demand of the people is essential in order to understand dynamically how to better manage this infrastructure and protect them. In order to ensure transportation, the highways and the road and the railroads are other very critical safety application in which the safety of the operation is important for the safety of people, as well as for a continuous flow of activities and in turn for the efficiency of the entire system. Smart cars, the adaptivities in smart cars is also important, as well as in the aerospace missions, since also in the airports, in the critical operation of airplanes, as well as in the space missions. In all this environment, creating an adaptive, dynamically adaptive environment is very, very important to ensure the safety and the comfort of people, as well as the safety of the entire system. Telecommunication is also important to manage properly according to the evolving needs of people, as well as all emergency services and rescue services, in which the understanding of what is happening in the environment may become very, very critical. And the ability of adjusting the behavior of the various components we have in the system can make the difference in the efficiency, the effectiveness, the capability of rescue people. Medical applications is another area in which the ambient intelligence can help, both in ensuring the proper environment for people, as well as the telemedicine, the robotics. All this kind of support can really save the life of people. But if we can go to our daily life, the use of this type of technologies in our home or in a building can improve not only the safety, but also the use of the energy, the sustainability of the system, and in turn make our life more comfortable and safer. We can also enlarge the vision and consider smart cities as a whole, where the proper monitoring of the traffic, of the lights, of the use of the energy, of the various services offered to the citizens can make a significant improvement in the quality of the life of people from one side, and from the other side can make much more sustainable the deployment of this kind of services. How we can use the technologies, but let's take a quick look to where the various technology I mentioned at the beginning can really help in implementing these systems. Artificial intelligence is really essential to create adaptive systems by considering neural network, fuzzy system, evolutionary computing, statistical machine learning, knowledge extraction, and many other reasoning techniques which allow to take the knowledge from the real world, from the real data, create an abstract view of the environment that we are observing, of the action in which occurs in the environment, and provide appropriate information to take the appropriate action in such an environment to address the needs of the people in that environment. In order to support this, artificial intelligence can be used in several phases, in several aspects of managing the environment. In signal and image acquisition, artificial intelligence can be effective for self-calibration, fault detection. In signal and image preprocessing, artificial intelligence can help in enhancing the quality of the signals and removing as much as possible the noise, which implies a much simpler operation of the subsequent activities, a much simpler configuration of the subsequent activities. In feature processing, artificial intelligence has also been shown effective, since we may not be interested in all signals, in all details of the images, but we may be interested in some characteristics which are in the signals and the images. For example, in the signal, the peak of the signal, the slope of the signal can be relevant since it is associated to the behavior of the environment. Neural networks, fuzzy systems, have been shown effective in this perspective. It is important also to understand how many features we need to consider. Few features imply a low complexity, but also a low accuracy. On the contrary, if we consider many features, we may not really increase the accuracy due to the fact that some of the features may be related each other by physical laws, and as a consequence, the addition of more features does not increase the knowledge that we can get. There are several techniques, statistical, based on artificial intelligence, which allow to extract exactly this information. In several cases, we may need to have a comprehensive view of the environment. We may need to put together different data coming from different sensors. And also in this case, artificial intelligence has been shown very effective for data fusion, or we may need to create virtual sensors using a sensor observing some characteristics which are related by the physical law to other characteristics in which we are interested in. And also in this case, artificial intelligence is able to do this mapping and create the virtual sensors. But another essential step after we have the data is to try to understand which is the status of the environment, which is the status of the action, what is happening in the environment. For this reason, artificial intelligence can be very effective to support classification, clustering, pattern recognition, starting from the feature that we have extracted. We need to control what is happening in the environment. We need to force the control system of the environment to adjust its behavior in order to satisfy the needs and the preferences of people who are in that environment. And neural-based control and fuzzy-based control has been shown very effective in this perspective as an adaptive and evolvable approach with respect to other more traditional solutions. When we have a complex system, we may need to identify many parameters, to set many parameters, and this may not be easy especially when we have many local minima and maxima in the function that we need to approximate. Artificial intelligence, specifically evolutionary computation, has been shown effective to explore the space of the solutions in a more free way, escaping from the local minima with many more opportunities. How we can support adaptivity associated to the identification of the people, to the specific profile of the people? Well, what we can do with the biometric techniques is to identify a person, so be sure who is the person who is in the environment, and as a consequence, we can be able to retrieve the profile associated to this person and use the needs, the preferences, the desires which have been stored associated to the person. And we can observe what is happening in the environment if this person expresses new needs, new preferences, so that we can adjust what has been stored with this new information. And we can also understand to which group of persons the individual we are observing belongs. As I said before, a young person, an elder person, a man, a woman, and this may enrich the characteristics of the group that we are observing. We can also understand just the action of people so that we can use biometrics as a sort of human system command and opportunity, like we type the commands on a keyboard. If I use gestures, the system can learn what a gesture means in the perspective of the specific control of the environment. Or my emotions can express possible needs, preferences, if I like or dislike what is happening in the environment. And this information can be used to adjust the behavior of the environment itself. Biometrics are a set of techniques which automatically allow to recognize an individual or the class to which, or the group to which the individual belong, as I say, the young, old person, man, woman, and so on, by using a physiological or behavioral characteristics of the individual. Typical physiological characteristics are fingerprint, face, iris, and these allow to recognize uniquely the persons. Behavioral traits like the gesture, the age, the gender, the emotions do not allow to really uniquely identify the people, but they can be used as feedback or commands to the environment. If we wanted to use these techniques in an intelligent ambient, in an adaptive ambient, we need to introduce more and more unconstrained biometric, or at least less constrained biometric, since we want to have the ability of using the biometric traits, even though the subject is not really cooperative, is not looking to the camera, staying still for a while to be recognized with the appropriate lighting and so on. We do want to work in an uncontrolled scenario without the contact for fingerprint, for example. I want to perform the recognition at a high distance or in natural light condition, or when people is moving, exactly as us as humans are doing when we see someone in the road, for example, and at a distance, and we recognize this person. Also in this case, we need to use signal image acquisition, pre-processing, feature extraction, data fusion, classification, and all of this is actually made available by artificial intelligence as well, with the adaptivity that we may need. Then we actually as I mentioned at the beginning, we needed to have the appropriate infrastructure to support the seamless use of these technologies in the intelligent environments for safety critical applications. Internet of Things is nowadays a modern, non-dedicated communication infrastructure which allows to put together, to connect sensors, other sources of data, for example, from mobile devices and so on, to the storage and processing that we have in the infrastructure, where we can store the data, analyze the data, extract the knowledge, and apply the appropriate control algorithm to control, to manage the environment. This, the Internet of Things is a generic infrastructure providing the basic definition of the services and at a lower level interfaces, protocol, the standards, which make the connection of the various components much easier through a plug-in approach. This structure is a generic support to any kind of application. Is essentially a communication infrastructure which is shared among various applications. The alternative approach is based on cyber-physical system, which conceptually has the same goal, but is specialized for a specific application in a dedicated way for architecture with components which are fully dedicated to one specific application, or in a virtualized way, where the connectivity is obtained by creating an appropriate connection which is dedicated in a virtual way to a specific application. Then what we need is also an appropriate place to store the data, to analyze the data, and to take the decision to manage and control the environment. The cloud computing is the modern approach which allows to do this worldwide in a very flexible way. The problem is that we may have a amount of data which are coming from the peripheral devices which may be really huge. And as a consequence, the bandwidth may not support the transfer to the cloud, where we have the algorithm, the program, the application to analyze this data and generate the appropriate control. For this reason, in many applications, another approach is more and more interesting, based on the concept of fog computing, where we move a part of the storage and computation more locally in the environment that we want to manage, for example, in a building. But if the amount of data to be transferred is really huge, we may even need to push the computation nearer to the sources so that we can actually drastically reduce the amount of data that need to be transferred to the fog or the cloud infrastructure. In any case, there are some aspects in this type of infrastructure which are really essential to ensure the usability of the intelligent ambient, to ensure that the entire infrastructure is supporting the users. Security and privacy is essential, since we do not want intrusion in managing the environment, and we do not want that the profile of the users are stolen, since these are very personal information. And we need to empower the users to finally control in a very accurate way which are the information of their profile that they want to share with each of the applications they are interested in. On the other side, we needed to have a high dependability and resilience of our system, since we do want to have continuity of service. And as a consequence, we needed to introduce enough redundancy in the infrastructure to achieve this goal. We wanted to have interoperability, the ability of adding components coming from different sources, as well as the scalability of our architecture in terms of environments that we wanted to manage, as well as a user for this environment. The last but not the least important aspect is the energy. We do want to create an intelligent infrastructure to support security of these safety critical systems, safety and the operation of these safety critical systems by minimizing the energy, so that the various operations are actually performed in the most effective way. The main contribution of this talk is therefore consists therefore in the fact that ambient intelligence can be achieved by putting together the various technologies I have been mentioning to create an effective, efficient infrastructure capable of adaptivity and capable of supporting a smart living for people. Thank you.
Thank you, Dr. Puri, for the wonderful session on ambient intelligence. That was very interesting. Hello, everyone. Welcome back. Now this was the end of our inaugural session, and now we will move on to the main part of the symposium. So that is the tracks. So the first track, that's the track for today, relates to modeling and design aspects of developing safety critical systems with artificial intelligence and machine learning capabilities. So to start off, we have a keynote address by Dr. Ravindra Gudi. He is currently the professor in charge of the IIT Bombay Research Park Foundation, and he has served as the head at Department of Chemical Engineering at the IIT Bombay. He is the AI and ML chair professor at IIT Bombay, and also the professor in charge of continuing education and QIP. He also holds the institute chair position in artificial intelligence and machine learning. I welcome you, sir, to give the first keynote address for today.
Thank you. Thank you, Aparna. I'll share my screen. If you can just confirm that you can see this.
Yes, your screen is visible.
Good evening. Good evening to everyone. Welcome to this first session on the modeling and design, the International Symposium on Artificial Intelligence, Machine Learning in Safety Critical Systems. I would like to primarily talk about the aspect of AI, a very peculiar aspect of AI, as commonly known or understood as artificial intelligence. But hopefully, I would like to be able to convince you that we could perhaps start recoining AI as augmented intelligence and machine learning, because machine learning is primarily to do with basically handling huge amounts of data, but artificial intelligence brings some cognitive reasoning and related aspects over and above what machine learning can do. And it's time that we bring in a stress and emphasize upon the domain knowledge, the importance of the domain knowledge, especially when you're looking at performance monitoring and performance improvement of safety critical systems. So let me begin. This is a quick talk outline. Over the next 20 minutes, we'll look at some of the monitoring aspects of safety critical systems. I'll very quickly allude to the digitalization and IIoT. I think the previous speaker did that to quite a telling effect. We'll look at some of the monitoring paradigms for fault detection and diagnosis and for performance monitoring. Through this, I would like to take two illustrative examples that primarily are very strongly associated with regulation and certification to bring the focus of safety criticality in this aspect of AI and ML. And then I'll present my summarizing remarks. So to begin with, when we are talking of safety critical systems, their design, their operation, we typically are looking at, especially during the operation, we're looking at designing from an optimality point of view during operation, trying to be as close to optimal as possible. But usually we are at a certain distance away from there for various reasons, either due to inherent variations or due to not a very robust and accurate design. We typically tend to operate away from there. And when there is an initiation of a fault or an aberrant operation, it would essentially go progressively towards failure. And this aspect of going from normal to incipient and failure is what I would call as a continuum region, because failure is something which is a yes or a no. I mean, is the manufacturing, is the plant, is the safety critical equipment operating normally? The answer is yes, you would be somewhere here. But if you say no, you would be somewhere here. But in between this, there is a gradual degradation also in performance, which we would like to be able to understand, model, and try to push the operation to be as normal as possible, but ideally as close to the optimality as possible. So what you see here are the two arrows towards fault severity and eventual failure, whereas here what we would like to promote is high reliability and performance as we go towards the optimal side of the performance. Now, when we do this, we basically have several sources of knowledge that we inherently use during the design step, but we tend to forget it at a later point. We, of course, have a good amount of knowledge about the physics of the system based on the mechanistic models. For example, in an aircraft, the 6 degrees of freedom, maybe in a chemical engineering application, it could be the mass and energy balances, like a boiler application and the like. So we can model to a certain extent or to a good extent the system and use it for design. However, this source of knowledge is not complete. There is a certain degree of incompleteness to this when we do the design. Likewise, measurements, of course, give you a lot of pulse. It gives you a pulse of the system. However, they need to be the sensors need to be located at the right places. They need to have relatively low noise, significant signal information, and be able to work. One needs to be able to work with a combination of signals to be able to infer about the health. This is what is exploited very strongly in machine learning when we try to characterize the performance of any safety critical equipment. And of course, another source of knowledge which is commonly ignored is the relative uncertainty between these two sources. Both of these sources are not complete. And you typically do have some idea of what is the uncertainty or the incompleteness with respect to these two sources. So we would like to exploit that in the approach that we take going forward. So basically, what does the design envelope give? It gives you performance limits, stability margins, and of course also resilience. How resilient is the plant to a variety of aberrant operations, exceptions, and robustness bounds. When you come up with a design and you start operating it, you are trying to drive towards optimality, but of course there are constraints on decisions. You need to work across all of this to be able to come up with, trying to push the overall operation of the safety critical equipment first safe, to be operating safe, and then towards operating in an optimal manner. So basically, when we look at approaches to extracting this knowledge, monitoring approaches have exploited knowledge from both these sources to define the safety envelopes. But safety and performance typically, most often, are complementary in nature. If you try to promote safety, you need to work with a relatively conservative performance and vice versa. However, if you bring in advanced model-based approaches, these could help improve performance even in the presence of aspects related to uncertainty and the like. There have been a lot of approaches depending on the extent of mismatch and uncertainty. It's common, for example, in oil and gas to do something called data reconciliation, where the mass balances are accurate, measurements are noisy. You reconcile the measurements to the model to get a sense of what's happening in the oil and gas area, especially when there is custody transfer. Of course, there's a very, very rich area, body of research in estimation and filtering, where the model is incomplete, measurements are noisy. You need to bring them together and be able to come up with ways of generating a statistically optimal estimate. Estimation and filtering plays a key role there. Sometimes the model may be very, very partially known and the measurements can be noisy. One could look at empiricizing what is not known, representing what is known, and that results into what's called as a gray box modeling, and then adaptation of the empirically unknown aspects of the model. And of course, the most commonly used approach in machine learning is, when the model uncertainty is high, poorly known, we have noisy measurements, you tend to rely more on the data generated, either using a black box, multivariate statistics, artificial neural networks, fuzzy reasoning methods, AI tools, and the like. So these are some of the approaches that are commonly known. And what we would try to do is, try to see if there is an opportunity now, rather than use only data, to augment and bring together the physics, knowledge of the physics, to be able to do a more reliable estimation as well as decision making. I would just like to take this first example of a safety critical system. Boilers, as we all know, goes through an extensive certification process. A boiler engineer needs to be certified to be able to operate a boiler. Now, here is an application where you want to maximize, let's say, the efficiency of the combustion in a boiler. You fire fuel, you have flue gases coming in here. Now, here have a diversity of sensors associated with fuel quality. The flame burns, it produces a hissing sound. You have acoustic sensors, you have thermal sensors. You have flame images. You could put a high-speed camera and image the flame to see whether it is darting, whether it's extincting, what is the volume of the flame, what's the color of the flame. Different parameters can be extracted. And of course, finally, you have emission information. Now, when you want to monitor this safety critical system, you would like to essentially establish first a benchmark. And that's where this combustion quality assessment comes into play. You look at a benchmark, for instance, the best known high efficiency combustion as a benchmark, and compare all the current operation with respect to the benchmark. Now, that's typically done in any database modeling approach. The question we ask is, can we do more? Answer is yes. You could essentially use a combustion system model, use all of this data information in a framework, typically a digital twin, keep this system model as close to the current operation as possible, and then query it for various decisions where you can actually do two things. You can push the benchmark higher to achieve a higher efficiency combustion, because there is no reason to believe that the best known high efficiency combustion, you cannot exceed that. There is no need to reason to believe that. So you essentially establish a theoretical limit as a benchmark, and then push your planned operation as close to that in a safe and optimal manner. That's where advanced optimization and control come in, recognizing the constraints associated with this problem, and then deliver a set of decisions that can essentially result in a high efficiency combustion. So this is one example, but I'll take a couple of others as we go later. How do we enable all of this? Of course, digitalization and IIoT. We all know about this. This is basically a science and technology enabled business transformation that brings in improved connectedness between different entities to promote safety and compliance, have improved productivity. And therefore, this digital transformation is one of the facilitators. Of course, we also have the framework of IoT, Industry 4.0, and then the wish lists associated with Industry 5.0 and Industry 6.0. As we do this, we essentially get elevated safety levels, data security, reliable communication without disruption in high integrity industrial environments, and of course, efficient and safe management of the industrial assets using predictive maintenance. So basically, all of this is driven towards safe operations, but also operation excellence. And so this connectedness that IIoT and the related frameworks bring in, improved connectedness, integration between different entities in the manufacturing or in the application, promote high productivity and operational excellence, which is essentially all of this. With this brief preamble, let me just take you to the first of the illustrations. This is basically associated with how we can extend machine learning approaches to also incorporate a physics-based model. And what I'm trying to do here is take an example of first the algorithm, which is generally very well known in machine learning literature. It's a multivariate statistical approach that reveals a lower dimension space. The algorithm is called principal components analysis. And what it does is, rather than view, for example, in this example, a fuel flow and steam demand as two separate univariate charts, essentially it does multivariate monitoring both the variables at a time and establishing control limits, which essentially helps you to identify aberrant operations like these, which would go undetected in a univariate monitoring sense. So principal components analysis is a well exploited tool for monitoring various safety critical applications. But what I'm going to show you here is how do we integrate physics-based information or models into principal components. One way of doing this, of course, there are several others, for an application that is associated with fault detection and diagnosis. How do we generate an early indication of an event, and how do we diagnose what is the root cause of the abnormal situation? So the idea here is to combine PCA, the principal components, with first principles knowledge to help reduce what's called as an average run length, which is the time between the initiation of a fault and its eventual detection. So let me just walk you through this quick example. This is an example associated with LDPE reactor, low density polyethylene reactor, the plastic that we use in day-to-day life. The reaction is monomers of ethylene combined to form a polymer. The temperature is 150, high pressures, degree of polymerization is very high. What's critical about the system is that there are side reactions that generate hydrogen. So there's a possibility of explosive reaction, also economic loss. It also generates methane. And so you would want to be able to monitor the operation of this LDPE reactor in ways that will help you to detect the explosive reaction that's happening and try to arrest it as soon as possible. This is a quick reaction schematic of the different measurements that are available. And now here is where we bring in the first principles knowledge. We know that there has to be an energy balance closure in this application. So this is a simple steady state energy balance closure that's written. And what's uncertain about this, we talked about model incompleteness. What's uncertain about this is the dependence of the enthalpy, the specific hits on the temperature. And so this uncertainty can be addressed by using principal components. So we just rewrite this in a typical PCA framework. We rewrite this energy balance in this manner. Now it exposes the temperatures, which are typically the measurements. And so one can try to monitor using PCA the closure of this enthalpy balance equation, because there are quite a few uncertainties which get absorbed into all of these alphas, and these H's are essentially the dependence on the measurements. So once we do that, we could perform a PCA on these H1, H2, H3, which are essentially the lumped components of all of these, and you look for an energy balance closure by establishing composition error limits on safe operation. Anything that goes beyond this is the danger of the decomposition reaction happening. We applied this on data from LDPE reactor. And what we see here is that the energy balance closure was found to violate the safety limits about 3 minutes before the onset of a decomposition. Ordinarily, with principal components alone, it would perhaps give you only about 1 minute lead time to be able to take corrective action. By incorporating the energy balance and monitoring the closure of that energy balance, it gives us certainly a much more lead time to be able to address that problem. I'll quickly walk you through this second, which is associated with pharma manufacturing. Again, as we all know, the pharma manufacturing is associated with heavy regulation around the operations of the pharma. Just very quickly to take you through this, basically we have a finite duration batch processes in pharma. And we want to advance this in chemical processes. This is quite routinely done through all of this. However, their adoption in the pharma industry has been a little slow because of the heavy regulation. So there are several challenges that exist from the process understanding point of view, and the regulatory mandates need to be recognized. However, with the paradigm shift in regulations, this basically is now facilitated in the regulatory structure. What's so peculiar in batch operations? It's a finite but variable duration in pharma manufacturing. Each batch might take, on an average, about, let's say, 1 day or 5 days. Let's assume that 24 hours, but there is an extent of deviation. It could take 20 hours to about 28 hours, and the average time is 24 hours. So it's a variable duration, finite but variable duration. In a pharma application, there are no sensors or minimal number of sensors because of the risk of contamination. Very poorly known or modelable processes. And the critical aspect of this is that there is a diminishing opportunity because there's a finite end time. There is diminishing opportunities for batch resurrection as we approach the end time. And so these are some of the challenges, and therefore there's opportunities to do mid-course correction for consistent batch quality. Just quickly show you first how data from the batch archive can be used. These are two quality parameters, yield versus time. you could essentially establish templates of best, average, and good from the batches that are already known and they are archived, the data is archived. However, what you could try to do is try to push all subsequent operation as close to the best as possible using mid-course correction profiles, which is what I show you through an animation here. And so that narrows down the variation between batch to batch, but also prevents the risk of contamination and improves the yield, which essentially is what is one of the key KPIs in a batch manufacturing. So here is a quick example of how this was done using the batch performance monitoring. Basically, you look at this as a statistical limit. This is a normal batch. A batch, when it is uncorrected, essentially goes out of the limits, and this is not a productive batch. However, if you are able to do mid-course corrections, exploiting data from archives as well as online data, one is able to deploy mid-course correction policies and bring a potentially unproductive batch also within normality. And so these are possible opportunities where you can augment the models, the physics from the physics as much as is known, adaptation based on online data from what is unknown, and continue to improve upon the fidelity of the model so that it could generate for you policies that promote mid-course corrections. I'd just like to then summarize, AI and ML technologies, of course, as we all know, have immense potential for monitoring safety critical engineering systems. We need to augment information in data with physics. As much as we know might be incomplete, so emphasize what is unknown, represent what is known. However, as you get more and more data on the fly, try to improve your empirical understanding. So this enables improved accuracy, of course, improved interpretability. This is one of the banes of machine learning algorithms, especially as you go into higher dimensions like support vector machines and the like. Interpretability, extrapolability are usually element factors in these. And of course, when you have the physics to as much extent as you can represent it, it could help you in regulatory, help you ease in regulatory certification. Therefore, newer paradigms incorporating prior physics-based knowledge are being developed right now. There are also several approaches that, for instance, bring together neural networks and first principles models to be able to come up with more accurate predictions, modeling related aspects. And therefore, this could, once you have a more accurate model, the direct benefit that you get, of course, is your adherence to constraints, and therefore adherence to safety norms is much, much more tighter without being conservative. And of course, as I said earlier, it also helps in regulatory certification. So this is what I wanted to present in the brief talk that I had. I'm happy to take any questions.
Thank you. Thank you, Dr. Goody. So I would like to tell the audience, if they have any questions in the auditorium, they could click on the questions tab and send their questions through chat. We will take those.
This is Yoga here. I have a question to Professor Goody. Professor, you mentioned about safety and the AI models, and then you're talking about PCA. Can PCA be used with the the physics models, and then can that be used as a safety around your AI? Is that possible?
Yes, there is recent literature on constrained PCA, for example, and the constraints could be, for instance, your physics-based models. If you look at the normal PCA, the PCA is basically an optimization problem where the principal components are canonically generated by maximizing the variance explained. Now that's the constraint is that each principal component must be orthogonal to the other, and you could pose it as an optimization problem to which you can potentially add physics-based constraints, and thereby the constraint PCA can actually deliver for you a solution that respects the physics as well as tries to exploit information from the data. We have just in the initial phases of developing these aspects.
Okay. There is still a lot of work to be done there, I guess.
Yeah, it's typically the trick is to be able to unravel the relationship between what they call as coarse and principal components and the original variables in the constraints that we write for that represent the physics. And there are ways to circumvent that challenge and be able to come up with a canonical. It won't be a canonical decomposition exactly, because there are multiple objectives now. You want to honor the constraints as well as you want to make it orthogonal. So there are some ways by which you can, come up with a compromise between these conflicting objectives.
Thank you, Professor Goody.
Do we have any questions from the audience?
I don't see anything on the chat here. There is one.
Yeah, there's one question.
Yeah. Check this question.
So the question is,
AI and other segments is possible, or it may take some time. We are already beginning to see now with the advances in computing and, when we are basically doing the modeling for monitoring or performance enhancement, we are primarily looking at solving optimization and control problems. And the advances in computing as well as optimization literature is increasingly making it possible now. It won't be long before we start incorporating physics-based reasoning, I would say. Typically, if you look at, for instance, neural networks or even the fuzzy logic related reasoning that you make, they primarily are, kind of based on data, if I would use a loose term, based on data, but they generally tend not to, because one has never posed a problem as such to represent the physics. But now now it's increasingly possible, I would say. There are ways by which you can represent this physics. It won't be too distant, Mr. Vivek, that we will start seeing AI and ML approaches that respect the physics. So that was my proposition that, AI is good, artificial intelligence, but it's probably also a need to migrate to augmented intelligence, where you exploit knowledge in the data as well as from the physics.
I had one question. This is Kiran Kumar here, Professor. I just see in many of the cases, when you are looking at safety critical and optimization, many times optimal approach optimization is for, if you are looking from efficiency or cost, that process could lead to less safe conditions.
Yes.
How is that to be handled?
Yes, that's precisely what I meant by, when I said they are complementary in nature. When we try to look at performance, it does not permit you a great deal of conservatism, which is typically required when you're trying to promote safety as an objective. We could look at ways by which you can bring in some kind of what they call as a lexicographic optimization, where you have a precedence ordering of your optimization objectives. For a safety critical system, obviously safety is first, and you put a safety envelope, the constraints associated with that, and within that envelope you try to promote performance. However, all of this is to a certain extent limited by the incompleteness of knowledge in the data and the non-availability or I won't say reluctance, but basically we are not using the physics to its full possible extent. The moment we are able to incorporate the physics as well as exploit the knowledge in the data, it could make our safety envelopes less conservative and also give more power to our productivity maximization or optimality seeking approaches, so that you are able to drive the operation closer to optimality while also honoring the safety constraints.
Thank you.
How can we generate the large amount of the corresponding variable for early detection of failures? Because all we usually have in abundance is normal performance. Yes, this is a classical unbalanced data problem. We don't have enough data regarding to fault scenarios, even known fault scenarios, let alone unknown fault scenarios. In unknown fault, we have absolutely no data. And so, for instance, in fuzzy clustering or fuzzy classification approaches, there are possibilistic, probabilistic, and credibilistic approaches to fuzzy classification, which essentially can look at ways by which unbalanced data can be incorporated. Also, novel faults. I mean, when you don't know anything about a fault, when you don't have any class associated with that fault, because you don't know that fault a priori, can these algorithms tell you that it's a novel fault? Answer is yes, you can. You would be able to say that this is a not seen data. Likewise, approaches such as correspondence analysis. We have worked a lot with that for fault detection and diagnosis. Correspondence analysis can handle unbalanced clusters extremely well. I would urge you to look this up. When we don't have enough information from the fault scenarios as well, we could, so the problem with that, when you don't have enough data about the fault, is that whatever we do with the algorithms tends to be overwhelmed by the normal data. But you can actually bring in record higher importance to the fault data associated with the faults as well, and then be able to represent normal as well as faulty data, and then do the diagnosis aspects. This is typically called as unbalanced cluster problem, but going further also for novel faults, there are approaches that can detect that this is a not seen fault and it's a novel fault.
So can we take one last question from Anita from Honeywell? I think there's a question previous to this. She says, I would like to know if it is possible to use these physical models and PCA for online learning setup in addition to training time. How do you think we can get good performance if used in online setup?
Principal components analysis is typically used for online monitoring. However, it's a data alone based approach where you look at archive data and develop the principal components and then compare online data with respect to these templates. If you want to do this using the physics-based model as well, that's what the example that I walked you through did. It basically represented the energy balance closure as a physics-based representation. It was not complete because the coefficients associated with the dependence of specific heat on temperature were uncertain. So those were estimated from data indirectly when we do principal components. There is a huge amount of data, those estimated, those alphas, indirectly in the form of templates, and those became the safe operation limits of the when you monitor for the closure of the energy balance. So indirectly, what you say actually happened in that principal components analysis for the LDPE reactor. But to directly answer your question, yes, as I was answering an earlier question as well, when you pose a principal components as an optimization problem with also the constraints being the physics of the system, there are ways by which you can, and we are beginning to work on that, right, on those aspects. There are ways by which you can get the benefits of both the knowledge present in the data as well as the structural relationships present in your model, although it's incomplete.
Dr. Goody, I think there are a couple of more questions in the chat. Maybe if you can reply on the chat, we can send those out to the people who asked the question.
Yeah, so maybe what I could do is I could just accumulate this and send it to me. I can respond to this.
We can do that, Professor Goody. Yeah, and then we can give it to the, in interest of time, we would request you to do that. Yeah.
Yes, thank you very much.
Aparna, continue.
Okay, thank you very much.
So, yes, thanks. Thank you, Dr. Goody. Thanks for the insightful session on the concept of augmented intelligence. And please accept this token, a virtual token from us.
Thank you.
So next we have Dr. Ramesh Bharadwaj. He's a senior researcher from the Naval Research Lab, USA. He is a researcher at the US Navy's Center for Excellence in High Assurance Systems. His research on rigorous engineering methods and tools encompasses the specification, design, and construction of tactical mission-critical systems, including communications, radar, and electronic warfare systems. I welcome you, Dr. Ramesh, to give the next keynote address.
Oh, thank you, Aparna. Yes. So shall I share my screen?
Yes, you can share your screen.
Okay, thank you. Let's see. Okay, so the talk I'm going to give is is called assured autonomy. So first, let's see exactly what we mean by autonomy. If I can advance this, that is. Okay, there. So yeah, so you already have given me, you know, an intro, so I will not belabor the point. I have worked at several research institutions, including TIFR, Stanford, AT&T Bell Laboratories with the Unix group, and Philips Research Laboratories, etc. And then my thrust right now is about AI and aviation safety. And so thank you for giving me the opportunity to present at the AIML Summit. So I use the term autonomy to mean something very specific, that is systems employing artificial intelligence, in particular machine learning, for their operation. And so we distinguish between automation and autonomy by saying that, you know, automated systems where users initiate or mediate every single action, and changes in the environment will not be explicitly handled by the system. It will need a redesign, versus an autonomous system can adapt to changes in the environment. It can even learn. So this is what we call online learning. But then there is always this hazard of, you know, saying this system will replicate human capabilities, you know, such as the unmanned drones that we fly. And then there's also an unmanned fighter aircraft that both the Indian Air Force, DRDO, and the US Air Force are playing with. And this is to replace a human being, like a wingman. And so that's fraught with other complications. There is also another deeply disturbing trend, at least among the US companies, where they realize that if you want to increase the accuracy of deep learning, then you have to like quadruple the size of the model. And so some of these, you know, really difficult model, you know, expensive models take millions of dollars to train, you know, so you literally need, there's a model called GPT-3 that took $5 million to train. So it's also a waste of computing resources and also a drain on the environment. It will cause global warming and such like. So there's actually a nice app that can tell you the impact of your machine learning algorithms on global warming, which I think you should try and look at. So it also needs a great deal of effort and expense. So for example, if you want to recognize a phone, you know, so I mean, phones have evolved over the years in many ways. So you cannot expect an AI to just realize suddenly that a slab of glass is also a phone. You have to explicitly say that. And so data curation is something that is very expensive, manual labeling, which can also have problems because you may mislabel the data. So we recommend that you only apply AI in situations where there is a potential for high payoff without compromising safety. And so this is something called data-centric AI development. So this is from deeplearning.ai. Andrew Ng, who was a professor at Stanford. And so you have to continue to keep training these models and then find out where they go wrong. And then you have to improve the data, which Tesla does that all the time. For Tesla, the error analysis is the people who actually drive these cars. So those are the guinea pigs who actually tell the organization whether or not the car is doing properly in certain situations. So I think I alluded to this whole idea of, you know, scraping billions of pictures, or this clip of OpenAI, or GPT-3, which has 175 billion parameters. And so they also have, you know, dangers. So for example, CLIP is something that conflates both the image processing side as well as the natural language processing side. So here is an example where, you know, it very nicely said it's a Granny Smith apple, which is, by the way, a kind of apple. But then you just have to put a picture, you know, a piece of paper which is with iPod written on it, and then it says iPod with 99.7% confidence. The same thing is true with a lawnmower, you know, versus a chainsaw. It says, oh, this is a chainsaw with 91.1% confidence. But then you just put some dollar signs on the picture, and then it says it's a piggy bank. So, so there are lots of reasons why people are exuberant about AI. You know, this is also something we call FOMO in this country, this fear of missing out. So we want to apply AI to almost everything. And when we say AI, it means ML-based systems. But of course, you know, I just told you how GPT-3 is hailed as the step towards general intelligence, but then, it actually makes some really egregious mistakes. And John McCarthy, who actually coined the term AI, he lamented that AI is harder than we think. And so Marvin Minsky, also one of the foundational players in this AI area, realized that easy things are hard. So we can navigate across rooms, we can walk around with a full cup of coffee without spilling it and so on. And this is really hard for a robot to do because we cannot specify what the problem is. And so, control theory can only go that far, right? And then moreover, I think the general public has been allured with all these wishful mnemonics, as I call them, which is, neural networks. Oh my God, this looks like the brain. Machine learning, machines really cannot learn, right? And AlphaGo's goal is to beat the best human player. AlphaGo cannot even think, right? Although it does beat the best player in Go, right? So this is an article by Melanie Mitchell, which I urge you guys to read because it's really a very nice article where she says why AI is harder than we think. So this is the levels of criticality, which is usually something that people talk about in the avionics industry. But here, if you look at it from the point of view of Netflix recommendation systems, all the way to nuclear reactor control, or also the kind of industrial processes that are controlled using AI that the professor was alluding to, they have different safety implications. So some of these systems are cyber physical, which means they interact with the environment. And so I think one of the dangers is that you take the algorithms being developed for the Netflix recommendation system and sort of just apply it to the mission critical or safety critical systems, which is a big no-no. So we want to make sure that you do not take these technologies that are kind of mostly work and not work all the time and try to apply them to safety critical systems. And so if you don't, if you sort of are very loose about the use of AI, this is what happens. Tesla's very famous accidents are really piling up. And so what is the antidote to irrational exuberance? We are asking these questions about which ones are safe and which strategies are reliable, which applications are trustworthy, and which methodologies are efficient, and which one is technology ready. So again, it doesn't mean that you shouldn't apply AI anywhere. There are clearly situations where you can apply AI, especially when you bring in these physics-based models that the professor was talking about. But then we will have three main challenges for autonomy, for assuring autonomy. One is safety, of course, which is very, very important, and this is only provable using logical arguments. You cannot say, well, this is a statistic. So if grandma becomes a statistic, that's not a very good thing, right? So you can say, oh, this Tesla only kills 1% of the people. Well, that's still pretty bad. And so there is also a Department of Defense Directive 3000.09, which you can download from the web, which talks about autonomy in weapon systems. And they say, unintended engagements or unintended functionality is what you have to prove the absence of, which is a tall order, especially when you have AI-based systems. And reliability, of course, is correct operation under suitable conditions, but they can easily change because of adversarial or natural shifts, which I shall talk about. And finally, we were talking about explainability and interpretability. And so I actually ran a workshop on this. And so my keynote speaker actually won a Squirrel Award. She just won $1 million. So that was very heartening. So what can go wrong, when you have a 100-kilogram remotely operated unmanned aircraft flying around near an aerodrome, which happened in 2019. And then the remote pilot lost control of the aircraft. And there was a kill switch, which you can see here, that was activated. And for some reason, it didn't work. Well, if you look at the way the kill switch has been engineered, you can easily guess why it didn't work, because it wasn't very well thought out, I would think. You got all these wires, sticking out of there and so forth. And then it crashed in a field approximately 40 meters from homes. And it climbed up to 8,000 feet into restricted airspace. This is an aerodrome with people landing, aircrafts and taking off. And so that was a very miraculous escape from a catastrophe. And so we can easily tell why the kill switch didn't work, but then can you tell whether the software works? And so I think this is the real problem. If you look at this is a call graph of some software that I pulled up from the web. I don't even know if the software is good or bad, or has it been well engineered? Has it not been well engineered? No one knows. Okay, so it's just a black box. And so therefore, the kind of activities that we talk about, like the thing climbing up to 8,000 feet and then falling, etc., we don't know. We don't know why that happened, and we have no idea whether the software can be proven to be safe under all conditions. And so there is also verification. So I come from the formal verification community. They say, oh, well, all you have to do is just verify this thing. But then we don't even know what the environment of the models are going to be like. So here is the case of a policeman in Italy who actually dances to regulate traffic. So when you have a self-driving car confronted by such a policeman or a whole set of bicycles, riders suddenly descending upon the road, no one knows what the AI is going to do. And then moreover, we don't even know what to say when we say avoid cars, because this thing, which looks like a snail, is actually a car. And then as we know, we have all kinds of things, vehicles. In Pakistan, you've got all these decorated trucks, for example. So how do you tell an AI and how do you characterize what it is that you want to avoid hitting, right? So here we have used a process-based approach. This is the SAE G34 EuroK WG114 working group. And so the first thing was, we put out a document called Statement of Concerns, that is AIR 6988, followed by AIR 6983, where we are actually developing a standard for certification and approval of aeronautical products that relate to safety critical systems. And so again, going back to the Airspeeder Mark II, we realized that it was poorly engineered and it was not very well thought out. And so we don't want to put such things in operation on restricted airspaces, especially without proper standards and certification. So the other one is something called, I call the alignment problem, which is, this mathematician Norbert Wiener said the disconnect between intention and result. So you may want the AI to do something, but then actually it ends up doing something else. And so the purpose we really desire is different from what it actually does. And so one of the things that was very funny was this faulty reward function. So here was a boat, an artificially controlled boat in a experimental, like a game, where the goal was to actually go and capture some object, at the end of the course. But the objective function was specified by saying you just have to maximize the distance that you travel. And so the boat just started going round and round in circles. It never really bothered to go in the direction of the actually intended target. But then if you have a human being, humans have what is called common sense, and they'll say, oh, clearly, this is not the way to play the game. But then an AI doesn't know this, right? So there is no common sense. And so you have to specify everything very, very precisely. And even if it gives you the right answers, it may be for the wrong reasons. So this is called the shortcut learning. So here's a case where the AI was able to perfectly tell the irises of humans as being from a woman or a man. It was doing this with complete confidence. But then it turns out that it was relying upon mascara. Usually women are the ones that wear mascara. So it was very confident that those are irises of women, simply because it was characterizing it not based on the shape and size of the iris, but actually whether or not the human being was wearing mascara. And so this is more insidious in the radiology. We have something called an artificial radiologist, which is highly touted at places like Stanford. And it turns out that it was telling the difference between melanoma or not, when a lesion is cancerous or not, based upon these purple dots, which were actually put there so that the surgeon can actually make the incision. So that correlates very highly with the thing actually being melanoma. So the AI was actually making use of the surgical marks or these drains to tell whether or not there was pneumonia. So it did the pneumonia detection based upon whether there's a drain put in or not. Okay, so that's, but then when we have this irrational exuberance, the Stanford website still says, they built algorithms that recognizes pneumonia better than human radiologists, and they've written papers and so on. I would expect that when they found out that these things were kind of done using shortcut learning approaches, maybe they should have fixed these papers. Just saying. Okay, and then moreover, it's easy to tell between cats and dogs. So if you look at the cat and the dog on the left side of this picture, we can easily tell that's a dog and this is a cat. But what about the one on the right side? And will an AI magically be able to do this classification? I guess not, because we have got these decision boundaries. And so if it is robust, it's shown by the green dotted line, then the big red blob, which is the normal set of data points versus the small red blob, which is this thing, which is, I think, a cat, I don't know, will not be necessary for global, even you have a global minima. If you're maximizing or you're doing a high hill climbing algorithm, then even the decision boundary, which is in black, is sufficient to get a good score. You can say, well, it's 99.99% accuracy, but then those little red dots and the blue dots are getting misclassified. And that's also because of the data labeling problem. Now, is the left side is a picture of a wolf. The right one, is it really a wolf or is it a dog? I don't know. Right?
The slides are not changing.
I'm sorry? The slides are not changing? Oh. Are you seeing it now?
Not yet. We are still on the alignment problem.
Oh, we are still on the alignment problem. Okay, so maybe I'll stop sharing and then I will share again. Maybe that might help.
Yeah, let's see. That might work.
That might work. Okay, so let's give this a try. Oh, so it just stopped at the alignment problem, huh? Okay. Okay, does this work now?
Yeah, it's saying now it will come.
It's coming up now.
You need to double click to enter.
Okay, adversarial examples. Yeah, I even shut off the video because I didn't want to have a large data rate, but it seems like the slides are not coming through. There's maybe like a bottleneck, data bottleneck or something. I'm sorry, I apologize for that. Okay, so so we know very well that these neural networks are fooled by adversarial perturbations, which means you can take a picture of a panda, and then you can just add some noise, and then it starts classifying that as a gibbon, although the human beings still look at the result as a panda. So these are the kind of things that we have to guard against. And so a stop sign can get misclassified as a speed limit 45 sign by actually painting some little dots on the stop sign. And similarly, this is called an adversarial patch. So a neural network that classifies a banana as a banana with 99% confidence suddenly says it's a toaster once you put this adversarial patch.
Slides are not still visible somehow, Ramesh.
Oh, is that right? Oh, I think it's probably my connection. I'm really sorry. Yeah. Do you guys have copies of the slide? I don't know. Oh, so you're not seeing anything.
Yeah, we are seeing a blank screen saying Ramesh has started screen sharing.
Oh no! Oh no! Okay, so let's try again. I'll say stop sharing. Okay, and then let's try sharing again. Maybe if I share the entire screen, it might work. I don't know. Let's try this. Okay, so is it working now?
Not yet.
Not yet.
Not yet. I think it's simply the data rate. It's simply not able to catch up with the slides. I'm sorry. I apologize. So nothing, huh? Not so far.
Nothing.
No.
So far.
Yeah. So I guess it's just the data rate is kind of low, I guess. Yeah. Yeah. So anyway, so just
audio.
Yeah. Okay. So then we will have to simply go with the audio. That's it. Okay. So anyways, so yeah. So there are ways in which these neural networks can be attacked, and recently Nicholas Carlini and others, they published a paper at NeurIPS 2020 where they took 13 of these defenses, adversarial defenses against defensive neural networks based on adversarial attacks, and found that 12 of these things simply do not work. Okay, so misclassification errors is like a huge thing. And so finally, for trustworthiness, we need to open the black box, as we call it. So because ML algorithms are inscrutable by human beings. And so explainability is really something where you take adjunct models and sort of, try to make sense of what the black box is doing. But we have to crack open the black box, which is what we call interpretability. And like I said, we actually ran a workshop this past March on something called trusted automated decision making, where we actually brought in all these experts to sort of have a way ahead for making the ML less obscure and more transparent. Yeah, so I'm sorry about the slides. So I will just stop there because I don't know if the message actually came through without the slides. We should have probably had a backup approach or something, some other way to share the slides. I'm sorry about that. Okay, so do you guys have any questions?
So,
what you have showcased.
Yeah, thank you, Dr. Ramesh.
I had just one question. What you have showcased
sure,
really tells us that there is still a long way to go with AI.
Yes, that's essentially what it is. So we should not just apply AI to any problem that we think requires a different approach. We have to be very careful, especially with safety critical systems, mission systems, warfighting systems, avionics systems, and such like. But if you're really talking about, maybe Facebook, then it's okay. We don't really have a problem if Facebook mistags a person as someone else. Well, except that, sometimes that may cause marital problems or something. If you tag a picture of someone being with another woman wrongly, then the wife might get upset or something. But for those kind of, so the idea is if you've got a cyber physical system, which means the system that actually interacts with the physical environment, then you have a big problem in terms of safety and other assurance challenges. So that's the takeaway here.
Thank you.
So in the interest of time, I would request the audience to put their questions in the chat, but we would take them offline and we would collate all the questions and send it to Dr. Ramesh so that we can get his replies on that.
Excellent. Yes. Thank you so much. And so, yeah, hopefully I'll also be able to share the slides with you guys, put it on some repository or something so that way you'll have them. Yeah.
Sure, that would be great. Thanks a lot, Dr. Ramesh, for the very insightful session on relating to the safety aspects of AI. And with that, I would like to call upon the next speaker, that is Mr. Satish Thokala. Mr. Satish Thokala is an aerospace and defense industry manager at MathWorks. He has approximately about 20 years of experience in teaching government and private aerospace establishments, including HAL and Collins Aerospace. So his area of expertise is avionics systems for both military and civil aircrafts. I welcome you, Mr. Satish, and request you to take the stage for the next keynote address.
Sure. Thank you. Thank you, Aparna, for the nice intro. Let me share my screen. Once for last time, can you confirm for both audio and video?
Yes, it's both visible.
Thank you. So thanks, first of all, thanks to AESI, INCOSI, and IEEE for giving me this opportunity. In this presentation, I'll primarily talk about my observations and learnings on aerospace and defense industry, especially highlighting some of the trends in terms of adopting AI, right? And also best practices from some of the early adopters of this technology, starting with leaders in this industry to the small and medium organizations. And what is the contribution from MathWorks in this technology field, right? So I'm sure most of you, are using MATLAB and Simulink in some or the other form, so which are our products, and MathWorks is our organization name. right? And thanks to the previous speakers for highlighting the systemic aspects, the importance of systemic aspects, and why it is important to test or verify the AI algorithms at the systems level, right? So in my talk, I'll focus on some of those aspects. So before, prepping myself for this presentation, I was thinking, okay, where should I start this presentation, right? Then if I do a bit of, traveling back in time, somewhere around mid-2010s, those days industry was really exploring the adoption of AI. So the challenges were all over the place, right? So which is kind of true for any new technology in its early days of adoption. But when I started grouping them, it started making more sense to me, right? So some of the problems are related to people, right? So no data scientists, there are skill issues, and we have data problems in terms of having more data, less data, how to store the data, what is the right amount of data that we can use to train the model. And then there are tool issues, right? So the tools, not just to build AI itself, but then how can we integrate those things with the systems around it, right? And also the business problems, right? So including what is a good problem, right? So thanks to the previous speaker for highlighting some of those aspects, right? So what is a good problem, right? And how do we demonstrate ROI, right? While implementing these challenges. As the time passes, right? And what you're seeing on the screen is some of the things that we're hearing from the industry now. And interestingly, these challenges are not only for aerospace industry, but these are valid across all the industries, including auto, electronics, right? So everywhere. Overall, if I just summarize this whole thing, overall, the major challenges are around quick, rapid prototyping of AI applications, integration with the larger complex system, and flexibility to include workflows from multiple vendors, multiple tools, right? Because there is no one particular tool set that can solve all your problems, right? And of course, also there are issues related to production challenges. How do we produce, right? Now, so clearly, based on our observations and based on our interactions with the customers, clearly AI technology is moving beyond the research phase and towards maturing towards deployment and implementation, at least for non-safety critical applications. When I make this statement, some of you may be seriously thinking about, then what about verification, validation aspects? How do I deal with certification aspects? What about explainable AI? I will talk about those things shortly in my talk. Now, let's do a bit of deep dive into aerospace systems and make it relevant to the theme of this conference track, modeling and design. The aerospace industry offers a spectrum of engineering, design, and development challenges ranging from sea, land, air, and space. So simulation and analysis of complex systems operating in such environments demands a streamlined multi-domain modeling workflows here. That's where the importance of bringing multiple domains into the systemic level really plays a critical role. And then how do we offer systems engineering to test or to hardware in the loop options, right, to support rapid design and development. So it's all about multi-domain modeling. So it's not just about AI, right? So how can we make sure AI is not going to be a standalone application end of the day? It has to be integrated with other systems or other subsystems. So how do we do that? How do we talk about multi-domain modeling aspects here? So I'm sure you would be doing your work in at least one of the areas that I have listed on my screen. So you could also see AI and data science as well here. So MathWorks value proposition here is we connect multi-domain engineering across your large organization with model-based design. I want to take one step back here and I want to ask you a question. What's the nature of your business? Is yours an engineering organization trying to solve a data science problem? If yes, then my talk would make some sense to you today. If yours is a pure data science organization trying to solve data or AI problem, then probably we may need to discuss separately outside this conference on how we can help you out, right? Now, continuing the flow. So from MathWorks side, we are building AI and machine learning into our standard workflows, right? That's how we are trying to make the work easy for engineering and scientists across the globe. so that we reduce the barrier to entry for domain experts, especially those who are working on engineering aspects and those who are looking to add AI into their engineering. Now, so how are we doing it? So how MathWorks is enabling these technologies. So how we started our journey. So most of you may not be knowing, our journey started in mid-90s actually, right? So with our initial release of Neural Network Toolbox around 1995, 1996, if I remember correctly. But the major releases started in mid-2010, somewhere around 2015. Since then, we have been releasing a stream of major updates that includes algorithms, apps, interoperability features to support machine learning, deep learning, and reinforcement learning. So here are a few application areas where we have built tools to solve engineering problems in the domains, using various types of data sets ranging from images, signals, audio, and text across various applications that you might be working on. And these verticals evolved tremendously since 2016. So here are a few customer success case studies that we closely worked with, where we helped them to adopt MATLAB and Simulink to solve some of their artificial intelligence related problems. Some of these things, the top three are related to imageries, either defect detection for A380 production at Airbus, or a Canadian company, Seacor, building an AI system to differentiate between icebergs and ships, and a Korean company, Crisho, using deep learning for object detection and tracking from drone images. And we also partnered with Domino Data Labs to help support Lockheed Martin's enterprise-wise digital transformation initiative. And when it comes to engine health monitoring, we supported Safran. And recently, we closely worked with Honeywell to build their machine learning classifier using a data set of 5 million records to verify their aircraft pitch control system that was built using Simulink. So all these customers had seen benefits using MATLAB in some or the other form. Some are quantitative, some are qualitative. But in my talk for next few minutes, I wouldn't prefer to discuss about what was achieved, what are the benefits that they had seen. Instead, I'll talk about how they did it. What's the workflow that they have followed to ensure success in implementing their own unique problem? How did they solve their unique challenge? That forms the baseline for rest of my presentation, which is broken into 4 areas. So start with the first theme, focus on engineering data. There are multiple ways we can synthesize data to train and test systems. If I take an example of wireless standards used in applications like 5G, SATCOM, right? So how do estimating the channel or detecting a router impersonation when you're working on cyber physical systems or for wireless LAN. And system and sensor models give you the ability to simulate sensors and platforms. For example, if I'm taking radar, so we can create radar Doppler images from a radar system. We can create the whole scenario and generate the synthesis and create data which we can use to train your AI models. And lastly, we can bring in 3D gaming engine-based simulations into MATLAB and Simulink for aerial and ground-based applications. On the screen, what you are seeing right now is how we integrated Unreal for autonomous systems kind of applications. So you can actually test your perception AI modules in closed loop systems. Right. Let's take one example to understand this better. So here I'm talking about simulating a radar at varying fidelity, ranging from raw IQ signals all the way to establishing tracks. And remember, this is all done in the modeling without actually needing the hardware to do this. You can actually model various sensors that includes IMU, GPS, altimeter, radar, LiDAR, sonar, infrared, and you can actually fuse data coming from these sensors and combine that with your real true data that you have captured from the field and use that data to train your AI models. You can also evaluate architectures that combine various levels of fusion here. Could it be at the grid level? Could it be at the detection level, at cluster level, or at track level? Second challenge in terms of data is how clean your data is. What I had seen, at least talking to some of the engineers in aerospace industry, the real world application of AI, it requires practitioners to spend more time on data prep rather than actually training the AI models. So here is one example for aerial surveillance, where you need to handle arbitrarily large images that don't fit in memory. So we can actually use MATLAB here and then see how can we fit these images, right, either in CPUs or GPUs. These tools also enable you to visualize, enable, and label this data. And of course, at some point of time to train your AI models. So various domains we can support when it comes to data labeling. So what you are seeing on the screen is one of the screenshots from Image Labeler app, which actually allows you to semi-automate the process of drawing bounding boxes around the objects so that you can start these labeled data to train your AI models. And you can also use it for pixel labeling by implementing algorithms, your own algorithms that works for the data set. So that would be my pitch for data synthesis. How do you process the data and how do you at least semi-automate the data labeling? Now let's move to the second part, the deployment aspects. So let me bring up an example here. This example is for a LiDAR system. And the goal here is to detect the objects using the LiDAR point clouds. So if you take a closer look at this particular system, when it is deployed on an existing compute platform, what we will see is different parts of this particular application would sit in different parts of the different pieces of the hardware. Say, for example, the pre and post processing are typically deployed on CPUs, whereas you might be using GPU to run your AI model or even to train your AI model, right? So then how do you differentiate between all these hardwares? How do you integrate the software that's running on all these hardware? Still, you will be doing systemic level simulations, right? And also these systems often need to handle different sensor inputs, right? In this example could be IMU, right? That can be used to filter out tracks from the LiDAR detection, right? So you can use some of the features that MathWorks offers to solve these problems, where especially you are dealing with heterogeneous sensors or you're looking into heterogeneous deployment options, right? Could be CPUs, GPUs, FPGAs, or even for that matter, cloud kind of environments. So here is a quick bird's eye view of hardware that we support. So you could see all big boys like Intel, Xilinx, NVIDIA, and also ability to deploy on cloud or edge platforms based on how it fits in your infrastructure, your organization infrastructure, right? So some of you might be needing to deploy these things in standalone hardware. Some of you would need to deploy these things on cloud or edge kind of systems, right? And we also have a close collaboration with SpeedGoat in case if you are looking for any hardware in the hardware in the loop kind of workflows. So that's about cleaning the data and then deploying your AI models. The next section is how to bring in systemic aspects, right? Here is where really the power of model-based design kicks in into your applications. So using Simulink, we can actually enable that to bring AI models into simulation where they can represent their hardware, what kind of test environment, right? And modeling different software and physical components like vehicle dynamics, and again, test the whole thing in closed loop, right? So in this example, so I have taken an example of automated driving domain. So in this case, the traditional vision detector algorithm is replaced using a deep learning model. And we are trying to run this whole simulation, right? So it's not just the deep learning algorithm. It is integrated in this test bench, right? And you are trying to verify or you're trying to test the functionality of algorithm in the overall system. So when I run this particular example, right, this actually helps you to see what's the accuracy that you're getting at the system level, and you're doing, before actually moving your entire design onto the hardware. Thus, you're actually increasing confidence on your design before you move the whole thing into the hardware, right, in the virtual environment. Right. Now let's go back to one of the questions that I asked, right? So what about V&V? What about certification aspects once we started talking about deployment in the field, right? MathWorks has a long history, as you all know, of enabling standards-based certification like DO 178C, DO 254, or ERP. We have multiple experts engaged with the committees at ESA or SAE G34, as mentioned by the previous speaker, and that involve AI workflows in aviation. This shows, if you look into the diagram on the screen, so all of us are familiar about the standard V cycle, but for AI applications, looks like the industry is moving more towards W cycle. If we have a closer look into this, the middle part of the W diagram, there is more focus on verifying the learning process. Unless the learning of the AI is correct, right? We can't expect right behavior in the field. I'm not even talking about unknown uncertainties where the model is not trained, right? But even wherever we have enough data sets, even the question is on how do we make sure that learning is correct, right? Additionally, we are expanding, our capabilities across our product line to support the standard as and when, industry is ready with the standards to adopt AI workflows. And we have similar engagements with SAE G34 that focus on AI as well. Now that brings me to the last part of presentation, which is interoperability. We understand and value the effort from open source community, which is actively working 24/7, right? So we have limited resources, we have limited staff at MathWorks, but the open source community works 24/7, try to bring in, new models, new AI models into the field, right? So we understand that. So and we provide interfacing mechanism to all these open source options. But before getting into talking about the interoperability aspects and then how exactly we do, engineering teams basically build AI systems, and when they are ready, they move that into production in idealistic scenario, right? But reality is sometimes you need a model that's built by some other team. Could be a data science team, right? That's working independently in your organization. So you would need to get a model from data science team. They might have used MATLAB, they might have used another framework, and you need to bring that into your engineering model. So interoperability bridges the gap between data science, engineering, and production. So using MATLAB and Simulink enabled workflows, you will be able to import and export networks and network architectures between MATLAB, TensorFlow, PyTorch, and ONNX. And you can also co-execute MATLAB and Python frameworks, as you need to do it. Right. Then the next point is, where does this fit in the DevOps view, right? So we're talking about deployment, but DevOps view, where does this whole thing actually fits in? So we can integrate the tool chains and technology stacks used by both IT and engineering personas in your organization. We can actually support end-to-end flow of the DevOps cycle that gives you visibility and control. So I highlighted on my slide, I highlighted some of the tools and workflows that we can actually tightly collaborate and bring them into MATLAB and Simulink environment. Now we can also integrate with popular data sources in case if you are using any data sources like Parquet or Avro, or also computing platforms if you are dealing with big data analytics like Hadoop, Databricks, or Apache Spark. So we can establish two-way interface with these platforms. And moving into operational side, operational view of this. So if you would like to stream the data from platforms like Kafka, we can bring in that into this environment, and also operational technologies like such as OSIsoft, right? So in essence, right, so one of the key takeaways that I want you to get from this talk is, so there is a robust framework and robust environment that's built around MATLAB and Simulink that would help you to solve your engineering data science problems, right? That provide close collaboration with multiple vendors involved, developing tools in this technology. So if that matters to any of you, our efforts are also largely recognized by Gartner Research. So MathWorks is identified as a leader in their magic quadrant of data science and machine learning in Aero for the second year continuously. So you could actually see MathWorks is appreciated for the completeness of the vision in this field. Right? Now, so I'm almost going towards the end of my presentation. So what are the resources for aerospace and defense industry to start with? We have lots of examples. I highlighted a few on my screen. See if any one of those examples would resonate with your work. So feel free to get back to us. Today in this conference, we also have a booth. Stop by at our booth to learn more on any of these applications. So as a summary, so we can actually offer end-to-end workflows for your AI applications to improve the productivity and finally to achieve a better ROIs here. So I have given my contact information on the slide. So feel free to send if you have any specific questions or you would need more detailed discussion with me or experts, AI experts in MathWorks. So thank you and enjoy rest of the conference today and tomorrow. That's all. That's where I end my presentation. Aparna, I'm happy to take any questions if time permits.
Thank you, Mr. Satish. So I think in the interest of time, we will take the questions offline. We are quite behind schedule now, I think. But yes, so let me just share the next. So Mr. Satish, so thank you again for the interesting session on the application of MathWorks tools for the AI-based systems, application of AI-based systems for aerospace applications. So with this, let us go on to the next part, the last part of the day one of the conference. So this is a panel discussion with on this particular track, which is the modeling and design. So I would like to invite the guests for this panel discussion. I would like to invite Dr. Darren Coffer as the moderator, to be the moderator of this panel discussion. Dr. Darren Coffer is a fellow at Collins Aerospace. His principal area of expertise is developing and applying advanced analysis methods and tools for verification and certification of high integrity systems. I welcome you, Dr. Darren, to be the moderator for this event. We also have a very esteemed panel, and among the panelists are Shri A.S. Kiran Kumar, who is Vikram Sarabhai Professor at the Indian Space Research Organization, ISRO, Bangalore, and President of the Aeronautical Society of India. He has steered the implementation of the applications-oriented Indian space program. He has played a crucial role in the Chandrayaan-1 mission and has made exemplary contributions to the success of the Mars orbiter mission as well. In recognition of his contributions, he was conferred the Padma Shri Award by President of India in 2014. Next on the panel, we have Mr. Ray Nicholas. He's the Director of Software Autonomy and AI Solutions at General Atomics, Aeronautical Systems Autonomy, and AI teams developing next generation autonomous command and control systems, autonomous processing, exploitation, dissemination systems, and on UAS, real-time AI edge processing for flight and sensor autonomy, air-to-air combat, and air-to-ground intelligence, surveillance, and ISR missions. Mr. Ray is also an executive committee leader for SAE Standard Works, which is developing in AI in aviation safety standards. Welcome you, sir, as part of the panel. Next, we have Mr. Robert Worosh, who is recently became the system safety lead at Merlin Labs, developing levels of autonomy for existing aircraft. He was previously the manager of engineering processes for Textron Aviation Inc., that's for Cessna and Beechcraft, aircraft and acted as a subject matter expert for the development assurance and system safety. Welcome, Mr. Robert. We also have Dr. Stacey McAllister, the AI and ML solutions architect at General Atomics Aeronautical Systems. Her work focuses on prototyping novel machine learning algorithms, developing machine learning algorithms using sparse, heterogeneous, or imbalanced data sets, and exploratory data analytics. Finally, we have Mr. Prashant Rao, who is the head of application engineering at MathWorks. Mr. Prashant is a strong believer of the fact that AI is more than just models based on algorithms, rather a complete set of steps that includes data preparation, modeling, simulation, and test and deployment. Prashant is among the top 50 AI influential leaders in India 2021 and was listed in the 10 most influential analytics leaders in India 2019, brought out by Analytics India magazine. I welcome you all to the panel, and with this, I would hand it over to Dr. Darren Copper to take over this session. Thank you.
Thank you so much for the introductions. So I think the way we'll proceed today, as we've discussed, is we'll give each of the panelists a few minutes to kind of make some initial statements and positions related to our question today about the what are the safety concerns for the use of AI and ML algorithms or techniques or components in aerospace applications. So let me kick that off with just a few thoughts, and I'll attempt to share some slides. Are you able to see this yet?
Yes, we can see it.
Okay, very good. I like to express this concern as perhaps getting things out of order instead of ready, aim, fire. You know, we have a great body now of theory, algorithms, and computing power available to implement machine learning. We've had many impressive capabilities demonstrated and even delivered in real systems, but perhaps not with the assurance evidence that's going to be required for safety critical applications, and in particular safety critical aerospace applications. And I feel like we're right now trying to catch up to bring the assurance story along with the capabilities. So here's our friend Elon Musk, and he had some interesting ideas about the use of machine learning at their recent Tesla AI Day, and this actually lines up well with a couple of speakers back, Ramesh from NRL, on when you should use machine learning. And Musk said, I discourage the use of machine learning because it's really difficult, and unless you have to use machine learning, don't do it. It's usually a red flag when somebody says we want to use machine learning to solve this problem. And I'm like, that sounds like BS. 99% of the time, you do not need it. So to be fair, this was in the context of ML use in the factory, but the admonition is even more true in safety critical applications. So a bit of caution, I think, is in order. So some of the challenges that I see just right off the bat are, and I think other speakers have mentioned these as well, we're used to dealing with precise, rigorous requirements in implementing safety critical systems. ML functional requirements are difficult to capture. Some of the image classification problems are an example of that. And we end up with large labeled training and test data sets as being more important than the traditional shall statements. Traditional assurance relies on requirements-based test cases with structural coverage metrics to assess completeness. Turns out these structural coverage metrics are not at all effective for neural networks and some other classes of machine learning. And then on the implementation side, machine learning design intent can't be inferred from examination of the inference model, making traceability back to requirements difficult or impossible. And furthermore, it means that we have no satisfactory completeness metrics for machine learning to detect or prevent unintended behavior, which I think is one of the key issues. Also, any implementations that involve GPU hardware are going to be challenging in onboard aerospace applications. A few use cases that are floating around within Collins, vision-based input for detect and avoid type of applications. And this brings us back to the requirements. Problem perception is a really strong point for the use of deep neural networks, but it's also the hardest to verify, both because of the size of the networks involved and the lack of precise requirements. I think we'll see some advisory systems providing pilot assistance with things such as route planning and weather avoidance. These are what EASA is calling level 1 type of applications, these advisory systems, and these will be the first things that we'll actually see probably getting certified for onboard use. Non-flight critical ground-based applications such as preventive maintenance and estimating remaining useful life for mechanical systems. Those are much less critical. And then I've been surprised to see that there's quite a few implementations that are really being done for efficiency reasons to reduce the compute time or the resource requirements. FMS optimization calculations, fuel measurements, the ACAS-XU system. All of these were done where machine learning was not strictly necessary to provide some capability that didn't already exist. There were existing implementations for all these things. But these are being pursued in order to make calculations faster and more resource efficient. And it turns out many of these we may actually be able to verify with some of the technologies that are being put together right now. A project that we're working on currently is bringing together a whole bunch of these new verification and assurance technologies. Here's an example where we're doing an autonomous taxiing application, and the guidance for this is being provided by a camera-based deep neural network that's estimating the position of the aircraft relative to the center line and providing input to a traditional PID control loop. And we are exploring, direct formal analysis of the neural network, anomalous input detection, test generation and new coverage metrics based on manifold techniques, and then runtime assurance architectures for independently monitoring the state of the system and the output of the neural network and detecting any deviations or unexpected behaviors and switching over to a safe backup. So all of these things are likely to have a role in the future. I think we'll talk more in the panel tomorrow about certification, but several of the folks in the meeting today are involved in this G34, SAE G34 EUROK Working Group 114, AI and Aviation Committee. And these new technologies that I'm mentioning will help, can be used to guide the new standard, be incorporated in some of the guidance that'll find its way into the new standard. But I think we still have residual issues related to requirements versus data, completeness and unintended behavior, and what exactly our hardware platforms look like for inference. So those are a few thoughts to start us out. I guess I'd like to turn it over to the other panelists, and we can start with Professor Srikaran Kumar, if you would like, and I will stop sharing.
Thank you. Thank you for that nice introduction to the topic for the panelists today. And as you have already shown in the space program or for the space activities, the current level of both AI and ML is not in a stage where it can be incorporated and we can go ahead. And as also one of the earlier speakers pointed out, that by nature, the space programs are much more, they take more time in adapting to the newer technologies and newer systems, simply because of demonstrated capability and assured performance requirements. So while that is in general true, but with the advances in the processing capabilities and the tremendous the advances that are happening in bringing in processors, what could happen in future is, as we are seeing with a large number of satellites in operation in space, the numbers start already running into thousands and tens of thousands. And if, as Elon Musk himself is looking at some 42,000 satellite constellations for operation, the scenario of traffic management in space could become an issue where this AI ML related requirements could be one of the key developments that would be needed for usage. And that's how probably things are going to happen. And beyond that, of course, when you start looking at more and more the fourth frontier of the space being the fourth frontier, and humanity looking at establishing new space stations or habitability places, encountering scenarios which are totally new, how to handle those scenarios could be the ones that could be coming up for AI and ML. But then taking into account today's discussion of safety critical systems using AI and ML, probably as already pointed out by many of the speakers, we still have a significant road to travel and then make use of it. I think these are my few initial thoughts. We could go ahead, and then if we have any specific questions, we'll come back later. Thank you very much.
Thank you. Ray Nicholas, would you like to go next?
Sure. Yeah, thank you for that introduction and your thoughts on this matter. So from a General Atomics point of view, you know, we're the leader in basically the mid-altitude unmanned aircraft area. So one of the things that our end goal really is to look at manpower reduction. So if you look at the unmanned space, you know, the way it's happening right now, there's a cockpit right on the ground that basically controls the aircraft via satellite. And typically we have one pilot, and then one sensor operator. And these aircrafts typically run like 30 to 40 hours at one time for one mission. We want to get to a state where there's from this 2 to 1 aircraft to 1 to many aircraft, right? So we're looking at everything from the ground systems to the aircraft and where we can apply AI ML. You know, we're starting to look at systems on the ground for our PED systems, helping the analysts using ML to make it more efficient for them to analyze a lot of the data and reduce the cognitive overload. We're looking at autonomy and denied environments. Basically, when these aircrafts lose communications, now the aircraft has to be a lot smarter in navigating to complete its missions. So, you know, we use ML in both sensor autonomy and flight autonomy. In terms of sensor autonomy, when we task an aircraft to a mission, there's a lot of sensors on board, right? But when you're running autonomously, we use AI ML to basically to place these sensors in so that you get the best sensor performance, for example. And flight autonomy, we're looking at different techniques to optimize flight path. And all this is all related to safety also, right? These aircrafts are like 10,000-pound aircrafts. They're very large. They're not these small little drones. So safety is very important. So we're looking across the board to help, you know, using ML to help us in every aspect of our business. That's all I have right now.
Thanks, Ray. Let's go to Robert Boris next from Merlin.
Hi. Again, I'm from Merlin Labs. I'm actually the system safety lead. I don't think it was also mentioned that I'm the chair of the S18 committee. The S18 committee actually defines and manages the system safety process and development assurance processes that are used in civil certification. And so even from that perspective, we are we have a dedicated autonomy subcommittee that is working on identifying the gaps in these conventional processes. And I think your presentation laid out very well, the challenges of where we're coming from. This conventional, I would almost say deterministic function, but a known function based on that we can kind of reliably demonstrate. And now we have a technology that we're putting in place where we can't 100% predict where it's going to go, how it's going to make decisions, and how do we bound that in the approach. We also laid out some very conventional approaches to how we attack the AI machine learning problem, in that we have to figure out what's to do with this. S18 committee works with the G34 committee, which is also in your slides, because it is a technology that fits within the systems of, it is not going to take over the whole airplane, especially starting out. And so, the initial approach is to fit it into a conventional system base or platform. And in partnership with the existing more normal autonomy systems, as well as flight crew, as you mentioned, advisory systems are normally the first place that we're going to see this growing. And so we have to develop the bounds within how that AI and the machine learning is being applied. And to that, we also have to figure out what is the best basis for determining what is safe within those limits, and how we can determine that the AI itself is protected against straying beyond those limits. So that goes from training of the AI to the bounds of a more conventional system, which may constrain its behavior, let's say. So there's a number of opportunities that we're looking at, and especially in the S18 committee, we're looking at the gaps of this conventional process where we talk about the function, and how do we have this, how do we bound the description of even what that function is when we have an AI system, and continue to allow it to learn. A number of challenges that are still being faced because that process of the safety process is what's being used for sort of being talked about in the next day. So all those things are deep considerations when considering the safety aspect of implementation, because it's not the whole aircraft, it's not the whole system. It's one aspect of a system that has to relate to the rest of these more conventional interfaces, especially in these early days of application. That's for me.
Thanks, Robert. Stacy, would you like to go next? Stacy McAllister.
Sure. Can you guys hear me okay? Thumbs up. Good. Okay. So I want us to, as we're starting to think about this problem, I want to keep in mind that, the whole goal generally of applying AI and autonomy is to invert the operator to machine ratio, right? We want to use these algorithms to, do things that would normally be done, using lots of time, lots of manpower, and lots of resources. And so with that, we have to think about, what does that system look like now? And there's a lot of human operators in there, right? And so ideally, like Ray was mentioning, we want to reduce the operator count and offload some of this onto the machine learning and other autonomous systems. And so with that, we can't necessarily forget the operator when it comes to verification, validation, and safety. There's a lot of things that go into the algorithms, like we were talking about, data sets, testing our algorithms, we're getting better at that. But we also know as practitioners more than, the general public, that these algorithms have real flaws, right? They have real issues with corner cases, and there's going to be instances, especially, like we're talking about in this early arena as we're trying to roll this out, that where it's going to encounter edge cases that it's not exactly going to be able to handle all the time. And when that happens, what happens in the system, right? Generally, we're probably going to kick it back to the operator and ask them to do what humans do best, which is, navigate uncertain, ambiguous situations. And so as we're designing the technology, we need to make sure that, we're getting buy-in from those operators. And, if they're controlling a fleet of, say, drones, and, 5 or 6 of them are having some issues and we alert them, how are we going to handle that task saturation, the task switching for the operators, right? So we also need to make sure that, as we're trying to offload some of this processing, we don't necessarily forget that, for the near future, there's probably going to be a human in the loop on this system. And so how do we also manage that type of interaction? Because that will be extremely important for safety and getting buy-in from the customers and the regulatory agencies.
Thanks, Stacy. Okay, and Prashant Rao from MathWorks, go next.
Yeah, thank you. I did have a couple of slides. Is that okay if I share them?
Please.
All righty, let's see if this works out okay. I'll just share my screen. I think that'll be easiest.
We're seeing that.
And you should be able to see the slides, I think.
Perfect.
All right. So, of course, one advantage is I just had my colleague Satish go right before this. So, but just to bring back some of the thought process that's there, especially approaching AI from a tool manufacturer, from the manufacturer maker of MATLAB and Simulink, essentially perspective, we see our role really is to empower engineers, scientists, domain experts to be able to use the right tools for the job that they've got in hand. And AI is another tool that is being used, or we want to enable engineers and scientists to use to develop their systems. That is the demand that we're seeing from the market, and this is basically what we're looking to enable. And we're very cognizant of that fact that AI models are part of the overall systems. The tools are being used to develop systems in traditional methods, and bringing in the AI part of it is really what we want to be able to do even better, so that basically engineers can prepare their data, understand the data, develop their AI models, understand why an AI model is working in a certain manner, simulate and test it in an actual environment, or as much as a real world environment as possible, and then deploy it to whatever system they would need to deploy it to. When you talk about deployment, there's, of course, the software industry or the IT operations industry has this whole cycle of DevOps, which has been working, and we see more and more engineers using these software development processes also within the engineering process as well, and then applying model development best practices to that whole software development cycle. We have model DevOps. Satish talked about this earlier as well, where we kind of go through an overall cycle where deployment is not the end goal. It's actually to understand from the feedback then, and actually then improve upon the model. Now, in the context of safety critical systems, this of course poses massive challenges, and we understand that completely. And that is where we talked about, building in steps in the traditional development V cycle to also include a step in which we can verify the model in itself and understand what was done in the overall training process for that model. Also in some way be able to recreate the training process in itself, so that it can be replicated using with different data as well. So really understand what is behind the decision making in that model. Of course, when it comes to formal methods on this part, we're still some way away. So when we talk about verification over here, this is really simulation-based verification. So where we're using simulation tools as much of a real-world environment as possible to be able to verify what is happening on the model. So that's in a nutshell, kind of taking from Satish's talk, adding a bit and bringing it together. This is what we're approaching, or this is what we're seeing from a tool vendor perspective.
Thanks. So since one of the questions I have is about, and this comes up in the G34 committee, is about the differences between the training model and the deployed inference model when you go to actually deploy an embedded environment. What do you think about the assurance challenges going from, we spent all this time developing the data and doing the training, yet that trained model is not what gets deployed. There's optimizations that happen. Do you have any thoughts on what the unique challenges are at that stage when we actually go to onboard embedded deployment? Is that different for these ML data-driven type of applications than the concerns we would have in traditional model-based development?
I can take. I'm assuming that's directly to me, right?
Yeah. Please,
there we have techniques that we use for code generation, and verification of code that is running on, actual deployed platforms. So whether it's running, let's say, on a microcontroller or DSP or a GPU or on desktop or in cloud, we can actually run that deployed model as it should be deployed and feed it with data off our simulation network or simulation environment. So we can verify that deployed model in the environment that it should be running in, but as a simulation as such. So one example would be, if you just go down the path of optimization, it could be that you go to fixed point, for example, for a specific model. We can run fixed point simulations. In fact, we can run it, process in the loop, so that we can verify the workings of that model in that real world, and then we even compare the results from the originally envisioned model with that embedded model, for example.
Okay, thanks. So that was a fairly low-level detailed question. Let's pop back up to a higher level concern. A lot of the, in my experience, the ML applications are, a really good system might be achieving a performance of 99% for doing, classification problems, or you'd have a distribution if you're trying to estimate a function in a regression problem. But we're still dealing with many fewer nines in terms of reliability or accurate, than we're used to seeing in safety critical aeronautics applications. How do we bridge this gap in the, here's this machine learning system that can give me 99% accuracy or reliability, but really I need something that's 99.9999 for a system component. How do we deal with that? Does Robert or anybody else wants to chime in with thoughts on that from this gap between what's achieved and what we need from a safety standpoint?
Well, from my perspective, so again, I'm from the system level, so it is a technology within the system, and when we talk about its, its the ability to rely on it for predictable behavior. It's really a method of how well we can demonstrate it, because that's not normally a part of even the safety analysis or the certification. Because the safety analysis, of course, we have this probabilistic aspect, and then we have this development aspect. And development aspect, in the conventional 178 is to reduce the errors in how we produce the program, right, or produce the software, which is not what we're doing anymore. So again, it's going to depend on how the AI, the machine learning, is applied in the system and in that context. And so we get into this problem of the engineering. Well, it depends, right? How are we containing it? Is it bounded by, again, a conventional system? And if that is the protection, then maybe there's more relaxation we can have on the AI, right? And that's, you know, in conventional certification, it's the iterative approach to developing that, because you're developing both the technology and the methodology at the same time, which is why we have to kind of more slowly increase the bounds of how we're demonstrating that AI and our methodology is appropriate. So, you know, I can't give you a straight answer. But what I can give you is, you know, that's why I think, as you pointed out in your slides, we start off with something conventional. Like you were saying, the advisory role would probably be the first one to be certified, right? Because that's bounded, because you have a pilot on board and you probably have conventional systems that wrap around it and bound it. Mm-hmm. And then from there, you can actually make the case that your demonstration, even though you don't hit all the nines that you need, is safe enough for that application. And then when you get to the next application, people grasp better both the technology and the methodology that you're using to demonstrate it. So sorry, it's a little bit of philosophical because it's a, you know, it depends scenario.
Well, that's what we do in panels. We are allowed to wax philosophical about these things. Well, so let me ask the same question really to the, you know, the concrete application folks, the General Atomics folks. And in particular, I'm thinking about the situations where, you know, you've got a vehicle and you have to be able to deal with a lost communication link and have this, have the aircraft continue flying reliability. What do you think are the challenges for the incorporation of ML-based systems that, you know, have some, you know, limits on their reliability, you know, perception systems or decision systems or whatever that, you know, aren't, you know, 100% deterministic or have a, you know, classification accuracy of 99%. How do you think will accommodate those kind of systems in your applications? Ray or Stacy, either or both, you have thoughts on that?
No, I'll take that first. So one of the approaches that we're taking right now is that we've got our safety critical enclave, right? So that's a very deterministic piece of the system. And then we've got a mission enclave where our AI kind of resides, right? So you kind of look at it as like, oh, we got this drunken sailor on one side that tries to you know, tell the safety, the good cop, you know, I want to go crashing onto a mountain, for example, right? Or some bad commands. So there's a checks and balances between these two enclaves, you know, that we're working towards. I mean, we're not there yet, and that's also going to help us get more confidence in the AI, right? And really, the more flights that we have, and we've been doing this, we're getting to the point where we're trying to validate everything in simulation, very high fidelity simulation. And then because we have a lot, you know, the aircraft, we can actually fly it in the next week, for example, right? And really build up the hours of flight and build confidence in the system. We have a lot of hooks and you know, checks on the flight critical side that validates everything you know, that's happening on the mission side with the AI.
Thanks. Stacy, anything to add to that?
Sure. So from a technologist point of view, one thing I would, you know, encourage is thinking about how are we structuring the problem, right? To piggyback off of Ray's answer, for safety critical things, we know we don't want the aircraft to, you know, fly into a mountain or, you know, do something outside of its flight envelope, right? We can put that added safety layer on top of that to make sure we get the deterministic behavior that we need, right? And for those type of, you know, safety critical systems where we know, you know, physical limits, rules, laws, kind of going back to your, you know, quote from Elon Musk, if we don't need AI there because we know the space, we shouldn't be using AI. But in instances where we know that the, you know, the behavior that, you know, we need the aircraft to perform, the added complexity of AI is worth the risk, so to speak. I would encourage us to think about, you know, how we're benchmarking that performance, right? So in those instances where, you know, we want the highest accuracy as possible, but we know that, you know, we're going to have to, you know, kind of you know, guide these systems along, so to speak, until we get that trust in them. Think about, you know, potentially how we certify and, you know, deal with operators right now, right? Think of actual pilots. We're not necessarily throwing them into the deep end right away, right? So while, you know, we have a test pilot or a student pilot, we give them, you know, a small part of the, you know, the mission or the, you know, a task list to perform. And so as we kind of get more and more confidence in them, they, you know, get more and more either, you know, data from their historical experience, or they get, you know, we have more trust in them. And so thinking about how we structure those problems in a way that we can deal with some of the uncertainty that we have in these systems right off the bat, I think is going to be extremely important to, you know, their deployment and our trust in them when we deploy them. So aiming for, you know, that super high accuracy right away is kind of a, you know, something we got to work up towards in the way we structure problems.
So Professor Kiran Kumar, are the concerns different in the space applications, or are we really talking about the same thing? When I think of the space applications, I think often about the delays that are encountered and also the need to be able to deal with lost communication and function in a very reliable way for long periods of time without necessarily you know, having intervention from the ground. You might have lost communication. Are there different are there unique aspects of the space applications that present challenges for machine learning? Oh, you're on mute.
Okay, sorry about that.
There we go.
Yeah. It's one of the key things, particularly for the deep space missions or the planetary missions, where you are likely to encounter a scenario where you have no communication. So one of the things that you are trying to do there is build into the system autonomy and try to deal with it. But here, of course, we know what to expect and we know the kind of scenario that is likely to happen. So it's all, again, in many ways, a predetermined approaches which have been incorporated into the system which is already up in space, which you are dealing with. But when you want to look at scenarios where you are going to encounter a situation which you have not anticipated, then you really do not know how to deal with that and how to overcome those problems. But otherwise, many of the cases, particularly with respect to loss of communication, it is a scenario which is fairly anticipated as one of the problems, and that could be dealt with in the current planning. But as things go along and as systems become more and more autonomous, we are likely to encounter scenarios where you have not anticipated, and for those unanticipated things, can you build in, based on AI and ML approaches, autonomy into the system and then come out with solutions. That is what would be the real expectations for the future.
Thanks. So one of the other possibly unique aspects of space applications, at least in my understanding, is maybe being more resource constrained than some platforms are in terms of you know, how much, you know, CPU or memory or whatever you might be able to deal with. Does that impact either the ability to use machine learning type of applications, or as I've been seeing, which surprised me, have you seen a demand for the use of machine learning in order to reduce your resource requirements? You know, somehow the machine learning implementation is more efficient than having a large table-based application for a decision application. Have you seen that type of demand?
Yeah, in the current discussions or during my experience of last many years, we have not really come across a case where you are trying to really optimize the resources based on this approach. In fact, probably it would be worth looking at for the future, but currently, most of the time, of course, if you look at our own experience, we are more resource constrained because of availability of the resources itself even the current versions which are there by virtue of the kind of constraint that we put on the system, established and demonstrated heritage. You are not even going up to the latest available resource, whether it's a processor or a system. So we have really not gone to those limits in that sense.
Very good, thank you. Let me throw out a general question for all of the panelists. A lot of what we have been talking about, and certainly for near-term applications, are what I would call static machine learning applications, where the training all happens offline, and then you deploy in the embedded environment a static, non-changing inference model of some kind. Yet, you know, one of the possible main advantages of machine learning is the ability to learn online as you encounter new scenarios, new inputs that were maybe not part of the initial training. Do you think that sort of online training application can be accommodated in safety critical applications? And if so, how? Anybody want to address that? Have you seen those kind of applications, or do you see that as a need or something that we're likely to see in safety critical applications?
No, maybe I can just take a guess. See, one of the things is like what you are pointing out. Definitely, if the online dynamic learning leads to some of the conclusions where those conclusions are well defined in terms of subsequent operation, as long as those dynamic scenarios conform to those ends, maybe it's a good idea to incorporate them. But if those dynamic scenarios lead to a situation where you have not encountered earlier, you don't know how to deal with it, that is where the real problem would come. Because the dynamic scenarios, what kind of dynamic scenarios you encounter, you may not know. But those scenarios, if they were to lead to a situation where there is a priori knowledge of how to deal with that end situation, that definitely I think would be a good approach for ML and AI, because those are scenarios which you have not anticipated earlier.
Anybody else have thoughts on that question?
This is Stacy, just to chime in there. I think the online learning aspect is kind of a double-edged sword, right? I mean, in one aspect, it kind of answers the question of once we deploy these models, how do we ensure that, you know, they don't, you know, get stale, so to speak, right? We know that once you deploy them, you know, you're probably going to have to update them. They're kind of like a pet, right? You got to care and feed them and make sure that, you know, they're still pertaining to the situation that they're deployed in. But doing online learning introduces more complexity, right? Like our previous panelist was talking about, if you encounter something that you didn't test for, you know, it could be outside the scope of, you know, the envelope of your previous training data. You're going to have to find a way to you know, deal with that in real time, right? Rather than in the lab when you're, you know, testing in a more controlled environment. So again, I think it comes down to complexity, right? Is the, you know, capability that you can get from that added complexity worth the risk, so to speak? And I think that's, you know, a conversation that, you know, people need to be cognizant of when they're, you know, interfacing with, you know, their customers, or when they're, you know, going through and designing these systems.
Yeah, I'll chime in there a little bit. I mean, this is where your modeling in SIM becomes very important, right? When we have models, we're using the modeling in SIM to kind of throw at a lot of different use cases and edge cases to help validate that model. But you know, it's a very difficult problem to solve in terms of safety. And then you've also got the compute resources. I'm talking in terms of UAS to be able to handle that. And right now, I don't think we have that capability. Technology is not mature enough.
New learning on board, yeah.
Yeah.
If I may just add that one thought, of course, that comes here is in the concept of the digital twin. So,
right,
you know, wait, you know, you have a twin running, you have a simulation modeler, you know, that you continuously improve through the data that you're receiving from the actual onboard device. The curveball, or in cricketing terms, the googly that you dealt was basically the aspect of safety criticality in this, which is, I mean, that verification has to happen before, of course, it's deployed. So that I think that's a tough part. But possibly the concept of a surrogate or a digital twin that's running, receiving data or integrating the data between the field model and the twin.
Right. So there, instead of having a kind of a tight onboard loop that's doing the training and updating, you've got this larger, slower loop where you're getting data from the onboard thing and training on the surrogate or the twin.
Yeah,
and then
conceptually.
Yeah.
Okay. Conceptually, that could be.
So one common thread that I think I heard in most everyone's comments was the need for some sort of bounding or runtime monitoring, or what runtime assurance architectures, where not just necessarily assuming or maybe we don't have the ability to verify a machine learning component to the same level of assurance as we do for traditional components, but we rely on some type of runtime monitoring and intervention. Do you think that is going to be a necessary part of safely deploying machine learning in these kind of applications?
As I said, and being from the system level, just even to get to certification, I think that's going to be a big driver, right? That is conventional approach, and that's the model that that would be the most successful. And I know certification is tomorrow, but in the certification way, but I think safety-wise too. I mean, we can be more certain, and in a way, especially when you're using it in an advisory capacity, the flight crew is that protection as well as with other systems.
Right.
So I think you have to start there and grow into it. And even with the online learning concept too, right? You would have to start that in a very bounded and specific way before you could do something to get to that safety critical aspect. I don't see a way to get there without stair steps of this conventional partnership with the AI machine learning.
Mm-hmm. Anyone else? Do you think this is runtime assurance going to be a necessary part of safely deploying machine learning, at least for our initial steps? Or are there other approaches? Are there applications where you've seen where we might be able to achieve the required level of assurance without this kind of independent runtime monitoring? Do you think that's a possibility, or do we see that are there any ML applications that are small enough or requirements are well enough understood that we could verify them independently of this sort of runtime monitoring wrapper?
Sure, I'll chime in on that one. And I think it all just comes down to risk level, right? So, I mean, a lot of stuff we're talking about, the stuff people gravitate towards when you start talking about, AI ML for, aerospace or, the flight sciences is, some of the more exciting stuff, right? But we realize that a lot of, the pre-processing work that goes into, getting, a jet in the air or, launching a satellite, there's a lot that goes into that, right? There's a big logistics tail. So for those type of applications where, the risk tolerance might be a little bit greater because the failure criteria are a little bit more soft, if you will. I mean, you're not, damaging equipment. You're not, you don't have as many safety considerations with, humans. I think these type of applications can make a little bit more inroads to start with as we start to figure out, how are we going to bound things for the more, safety critical, risk averse areas.
Good, thanks. Okay, well, I think we're getting near the end of our time here. Any of the panelists have any other thoughts or comments or concerns to share? Any other things that we haven't covered yet, or anything you would like to respond to before we wrap up? So, well, let me just summarize some of the things I think we heard here. I appreciate everybody's, or also let me just say, are there any questions from the audience that we want to grab here in our last couple of minutes?
There were no questions as such, only some comments were there, but they are not questions, I think. So you could summarize, yeah.
Very good. Okay, so I think, panelists, thank you everybody for joining us today and for your contributions and insights here on this topic. I think as we've seen, there's a lot of enthusiasm for what machine learning might be able to bring to our domain, but I think we have all expressed that we want to have realistic expectations for what can be done or what our initial steps ought to be. I think we'll see more modest application rather than these giant, science fiction type of applications of AI and machine learning, things that are a lot more down to earth, less safety critical, things moving from the, and certainly the offline trained, statically deployed systems are going to be more the most realistic, the things that we'll see in the near term. The idea of using traditional high assurance systems to monitor and bound the uncertainty that we might see in a machine learning application that's not going to give us the reliability that we might need in aerospace applications seems to be a common theme that we should expect to see in deployed architectures. And also separation, the different enclaves that Ray mentioned about the really flight critical, safety critical enclaves where we're restricting ourselves to deterministic, traditionally developed systems, the good cop, as he said. And then hosting machine learning applications in a separate enclave where you the safety concerns are possibly less. I've also seen that sort of architecture and proposal, and it seems very very likely that that'll be the way forward in the future. And then Prashant gave us an overview of the tooling and process that they see. There's so many parts of that are going to be different from what we have in traditional systems, data curation, and the verification of the training process, and moving from training to inference models that are deployed, making sure that I think the terminology that we use in the G34 committee is the operational design domain, making sure that the trained system is within the domain in which it's trained to be competent in detecting when that is or is not the case. That'll be an important part of the deployment of these systems going forward. So I think that's about it, and we're at the end of our time. Again, thank you everybody for joining us, and to the audience for listening today.
Thank you. Thank you very much.
Thank you.
Pleasure.
Thank you, Darren.
Thanks, guys.
Thank you.
So I would like to thank, with this, I would like to thank Dr. Darren Koffer for the moderating this session and for your valuable insights. And a big thanks to the panelists for an engaging and insightful panel discussion, raising some pertinent questions on AI and ML applications. So with this, we have come to the end of today's session. And I would now like to ask Dr. Yoganand Jeppu from Honeywell to summarize today's discussions and sessions. Over to you, Dr. Jeppu.
Thank you, Aparna. So it was a great session today, and I think we learned quite a lot. And I would like to just summarize. So we started with Kerry's lecture talk on AI, and what I was impressed by was the two cones she showed, the plus and the positiveness of AI and the negatives of AI as two inverted cones. And then when we went through the whole talks, the different talks, we were either in the top cone of the positiveness or the bottom cone of the negative. So that was the general trend that we saw, in the complete discussions that we were listening to. We had the talk from Sabyasachi from Collins, and something interesting he mentioned was that he did his master's in neural networks, and then he was talking about this tank with the AI in loop, and so this AI, is another soldier. So there is one soldier less, and this AI is assisting the other two soldiers, in the war footing. So that is a kind of reliability of the AI system. And then we had Dr. Satish Reddy talk about DRDO, and what was very nice thing that he told was that every systems laboratory under the DRDO umbrella is going to have an AI group. So that was something very interesting to know, as well as the way he is encouraging the students to, have an incubation center in their college, and how, they could perhaps contribute, and the amount that he defined was, absolutely huge. So I think the positiveness of DRDO in encouraging AI among the student community in India came out very well there. And then we had Professor Vincenzo talk about AI in the medical domain, the railroads, the aerospace, and all the safety critical systems where AI could be used. Professor Goody attributed the A to the augmented intelligence rather than the artificial intelligence. So I think that makes a lot of sense that, you are not talking about, replacing human intelligence by something artificial, but you're trying to say that the AI is an augmented intelligence, which works with the perhaps the human intelligence. And Dr. Ramesh, he talked about these challenges and how AI can fail, and something it's talking about how it learns, about the eyelashes, and we call it kajal here, that the ladies would apply, and how it learns that rather than the different. So it learns something different. So the data that is used to train is so much more important. And he was talking about how it has learned that, surgical mark. So instead of that, it has learned from the surgical marks on that this, this image has a problem. So we need to be very careful here. And Satish from MathWorks went through the whole tool process and the maturity of the tool chain that is there that can help us make these AI models and deploy them. And then we had this fantastic panel discussions, and which was very nicely summarized with Dr. Darren, that we require AI, but we need to have a bound around the AI, perhaps using some traditional methods so that we know that we cannot go wrong as such. With this, we end this today's session. Tomorrow is another fantastic session of 4 hours. We start at about 4 p.m. and our platform will be open, so you have about half an hour to visit the stalls, and Then we have at 4:30 the normal, discussions and the presentations. So we have, many guests. We have the, George Romansky from FAA, and then we have Dr. Brown from Raytheon, and we have Ritesh from FAA again, and Dr. Seema Chopra from Boeing. So they are all going to talk about certification aspects of AI. And then we have again a panel discussion where we are going to discuss about the certification aspects. Today we were talking about the usage of AI, and tomorrow it's going to be about certification aspects. And then we will end tomorrow with Raj Pai's talk. Raj is from NASA with his talk on the, as a valedictory address. So thank you so much for being with us today, and hope to see you tomorrow also. Thank you very much. I would like to thank all the panelists. I would like to thank all the speakers who were there with us. Thank you very much.